the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The broadcast is now starting. All attendees are in listen-only mode.
Hi Linkesh, good to see you.
May we are live?
Yes. Hello everyone, a warm good morning to all of you. So we'll wait for a couple more minutes for the rest of the participants to join.
Yeah, a quick audio check before we start. Can some of you please confirm it in the chat if you are able to see us, hear us properly?
Is my video coming now? Now, because I had to change something. Yeah.
Yes,
Yes,
Shana.
yes, Shana, it is. It is up.
Okay.
Can one of the attendees please type in the chat if everything is good? We can hear us, we can see us.
Yeah, people are responding in the chat saying yes.
Oh, okay. Oh, okay.
You can- Yeah.
Okay, so we'll start. I see the students are joining in, but we'll start. I think they'll join in the meantime. All set? Okay, so again, once more, good morning to all of you and welcome to the Bootcamp of EV Hackathon Season 3 Hackathon. So we've had registrations from many colleges across India, and I'm happy to see a good number of you have already joined, and I see more participants joining us again. So we have planned a long and exciting day for you guys. So I hope you've had your breakfast and you're all set for the day. So without further ado, let's officially start the event. My name is Ameya, and I'm one of the engineers working here at Bosch, and I'm also one of the EV Hackathon coordinators. So I'll start by giving you a glimpse on why we have organized this bootcamp. So right now we have 341 attendees, the students in the call, and you're all from different engineering backgrounds, different colleges, different states. So that is like a diverse background and experiences. So there might be a team who have had an experience with attempting to solve problem statements like this before, but there must be a lot of teams who's completely new to this. And moreover, we believe that the most hardest part of solving a problem is to start attempting it. Like we have observed a lot of teams who spends a lot of time in researching what to learn rather than attempting to solve the problem. So we wanted to bridge this gap here, and that is why we're providing you this hackathon. So we're basically providing you all the resources that you would need to get started with the problem statement. So I know it's a long session, but I promise you it would be interesting, and you would be leaving today with a lot of new learnings. So all we are asking is your undivided attention for the day, and we can all promise that you would be all set to start working on the problem statement, to start cracking the hackathon. So with that, let's move on to the much awaited inauguration event of the day. I invite Mr. Shanoy RK, who is a member of executive leadership team and senior vice president of mobility engineering at Bosch Global Software Technologies. So over to you, Shanoy.
Hi, good morning, everyone. Good morning, students. It's indeed my privilege to be part of this event today, where great minds, passionate minds come together. Of course, it's quite early today, and I'm sure all of you are well geared up to be part of this interesting one. Thanks for those who have this interest and curiosity to join this event, which is, of course, a flagship event of Bosch, the EV Hackathon. And over the years, I think it's gaining much more traction. Embarking on the path of sustainable future, we see the future of mobility, of course, defined by pillars of PACE, as you all know. And that's personalized, automated, connected, and electrified. Among those four, of course, trends, it's clear that electrification stands out as a key pillar towards sustainability. We have been, of course, innovating in electrification over years. There are solutions out there on the road, and even much more being developed currently in our centers. And many people like you are part of this development. But much more needs to be done to make it more efficient, to be much more cost effective for worldwide applications, as well as specifically, of course, for India. Towards this vision, of course, the EV Hackathon is a unique platform dedicated to identified exceptional minds who can develop excellent solutions for the future and preparing India for the greener mobility. Over the past 2 seasons, I think, as already mentioned, we have witnessed impressive turnout of more than 4,000 students and almost 40 of them are exceptionals. And these exceptional students individuals have joined Bosch, actively contributing in live projects, developing new solutions. In fact, two of them, I'm proud to say, have already contributed in the innovation and also filing IPs in this space. It is my utmost privilege to inaugurate the third session of this flagship event, where we have received overwhelming response of almost 4,000 plus across India, and I'm confident that this one will be even better than the previous two events. Today we are delighted to host this one-day bootcamp where experts will train all of you, the blooming minds, on the electrification journey, and I feel deeply honored to be part of this to inaugurate. Thanks and wish you all the best. Happy learning and happy applications of your minds for innovating for India and the world. Thanks a lot.
Thank you, Shamaik, for inaugurating EV Hack 3.0. Next up in line, we have one of our... next up we have in line, I would like to introduce Mr. Yusuf Osman, Vice President Engineering for Electrification. He is the man who spearheads the entire electrification section here at Bosch Global Software Technologies, with great competencies in system engineering, mechanics, hardware, and software. So, Mr. Yusuf Osman, over to you, please.
Thank you, and also good morning from my side, dear students. First of all, let me express my thanks to all of you. So we are really overwhelmed by the great interest from you for this electrification hackathon, which is an exciting platform, where brilliant minds like yours come together to create innovative solutions for a sustainable future. So I'm thrilled to see your enthusiasm and commitment to making a positive impact. Electrification is the key to transforming our energy landscape. It offers us an opportunity to reduce carbon emissions, combat climate change, and create a cleaner and, of course, greener world. Today, you have the chance to be at the forefront of this exciting journey. As students, you are uniquely positioned to drive change. Your fresh perspectives, innovative ideas, and also your technological capabilities can shape the future of electrification. And this hackathon, and today this boot camp, is a platform for you to unleash your creativity. So collaborate with like-minded individuals and come up with solutions that will make a difference. Remember, electrification is not just about technology. It is also about people. So during this hackathon, embrace collaboration. Engage with your fellow participants, share ideas, and also learn from each other. Seek guidance from the experts and mentors present here. So their insights and experiences will enrich your journey and help you develop innovative and also impactful solutions. Be bold, be daring, and be resilient. So innovation often comes from taking risks and pushing boundaries. So don't be afraid to fail. See it as an opportunity to learn and to improve. Embrace challenges, think creatively, and never lose sight of the bigger picture, the future we are striving to create. So finally, remember that the journey does not end with this hackathon. It is just the beginning. Take the lessons, connections, and experiences you gain here and continue your pursuit of electrification. Be ambassadors of change, driving awareness and inspiring others to join this movement. In conclusion, I have the utmost confidence in your ability to make a difference. As you embark on this electrification hackathon, let your passion ignite your ideas, let your knowledge guide your solutions, and let your determination fuel your success. Thank you, and may this hackathon be a catalyst for a sustainable and electrified future.
Thanks a lot, Yusuf. Indeed, electrification is the future of mobility. And with that, let me call upon our next person, who's Praneeth and Reddy. So he's part of the HR team here at BGSW, and he also handles the university relations topic. So over to you, Praneeth.
Thank you so much, Amaya. Thank you. And good morning once again to all the students. I know I love talking to students, so I generally get carried away, but I'll try to keep it as short as possible. Yeah, so I'm really happy and privileged once again this year to welcome you all for EV Hack 3.0. If you look at the way the EV Hack has been a success for BGSW and IEEE is phenomenal. Like, for example, last year this year we didn't expect the registrations to go this huge. And in fact, Prashant and team, we had a lot of struggle internally to decide upon should we extend the deadline or should we continue with the registrations and how do we go about it. And even in terms of the problem statements, we have expanded this year compared to the last. So yeah, at BGSW, we always believed it's not just a transactional relationship that we would want to have with students, fraternity, or even colleges, where we generally talk about hiring, internship, and etc. We strongly believe in collaborating with the academia strongly in terms of various ways, and this is just one of such platform where we partner with organizations like IEEE to create a platform for enthusiasts across the country to participate and showcase their talent. So this bootcamp today is going to give you a lot of insights in terms of various technical aspects to help you learn a lot of new things and perform better in the hackathon. And at BGSW, we are really looking forward to host you all and give you a great experience to this hackathon. And thank you so much to my colleagues at Bosch, especially Amaya, Jason, Prashant, who made this happen, and also the IEEE as a partner to enabling this at a large scale. Thank you so much, guys.
Thank you very much for that, Praneeth. Now, our next panelist for this inauguration is none other than Ms. Sarada Jayakrishnan. She's currently General Manager at Thermo Penpal Private Limited with over 20 years of experience in industry. And not just in industry, she's also been the past chair for IEEE Kerala section. When we were talking to our IEEE colleagues on who should be from their side to inaugurate the session, the answer was very unanimous, and we had Mrs. Sarada Jayakrishnan as the panelist. So let me please welcome you once again, Mrs. Sarada. Please take the stage. We would love to hear from you.
Thank you for that very kind introduction, Christian. Good morning, everyone. It's so nice to see Mr. Shenai, Mr. Osman, Prashant, Praneeth, and many others probably I've met earlier also. So thank you for the opportunity. And it's indeed great that I remember we had started the first edition when I was a chair of Kerala section, and there was a connection that we built with Bosch through various team events. So once again, very happy to be part of this panel. And a very good morning to the students. I was listening to what Osman was mentioning about taking innovation and risk. So I'm very glad that there are more than, I see, 480 participants already in the panel. So I'm sure these students have taken the first step to be creative, to be part of this hackathon. I don't know if all the students are from IEEE. Just a quick introduction. IEEE is the largest pool of professional engineers world over. And Kerala section, where I represent, is currently close to 16,000 plus members. And 80% is students. So students is our biggest strength because they are the next generation and where all the hope resides. As many of the speakers previously mentioned, there is a lot more to be done on sustainable energy and other innovation. I'll quickly touch upon some of the collaborative aspects we have been moving ahead with the industry, specifically from the section side and also on the India Council side. Why I thought this is relevant is See, compared to the developing nations, let's say USA or the European countries, the collaboration between the universities and the industries is not as tight as it should have been in this part of the world. It is really improving. I know a lot of universities where they really collaborate. One of the best example I would say in Kerala would be Amrita University, where there is, lot of interventions and collaborations to look at solutions that are really required for the industry and not just bring in some research which will never see the light of the world. But then there is a lot that we keep saying that maybe the government should do this, do that. Yes, government platforms are there. I'm speaking very specific to Kerala because I thought from the section level that's very relevant. See, Kerala has brought in interventions like KDISC, which is for bringing in knowledge-based solutions and interventions with academia and industry. There are specific platforms because I work in a medical device area. There are specific platforms like the Kerala Medical Technology Consortium. That's an ecosystem that's striving for an ecosystem to bring in, small entrepreneurs, big players in Kerala in the medical device arena, universities, and see that the researchers that the universities see are brought to maybe an entrepreneurial stream. So this ecosystem is slowly building up. There are many others like the startup villages across the country, the maker villages across the country. But then there is a major role that professional bodies like IEEE has to play where we can really bridge the gap between industry and academia. So for the students, interest to the students, when we say IEEE, it is a large pool of academicians, majority are academicians, at least in India. Maybe because of the reason that there are some incentives associated with joining a professional body like this, especially in their PhD, in their, the learning skills that they need to keep on moving. But then that is also a platform where you can, I was listening to what Osman was saying, anything that is where you can, draw the knowledge, that should be utilized completely. That is something that sometimes we miss out. We will probably do a hackathon, you may come up with a solution and that's it, you will just leave it. Don't leave it. Maybe Bosch will take the solution, Bosch may not take the solution, but you can stride ahead with the solution. It can be part of your project. You can drive with you could be an entrepreneur later on. There is a lot of, support systems that Government of India, Government of Kerala is bringing in and other governments I know to see that you all thrive. So the important message for probably the students here is learn, keep learning. There are so much of opportunities, especially with industries like Bosch. We have close to our place a lot of IT industries like Tata Elxsi, UST Global. Then there are major players like our electricity board, where we were talking about electrification. There are some small interventions where they are also supporting IEEE in. There are other areas like ISRO, VSSC, where they have the whole platform available for students like you to partner ahead. So I'm very, very happy to be part of this inaugural event. All the very, very best for the students. We really look ahead that through good solutions, which could be products really, or enhancements to products come out of this hackathon, and you all have a great learning experience. Thank you so much. Thank you for the opportunity again, and it's my honor to be part of this event. Thank you.
Thanks a lot, Sharada. Truly, the opportunities are endless and sky is the limit. I wholeheartedly agree with you. And next in line, we have Mr. Sajid CP, who is the Head of Engineering of Powertrain Electrification at BGSW. So he would be addressing the students on the inspiration behind EV Hackathon. So over to you, Sajid.
Yeah, thank you. I'm being heard, right?
Yes, we can hear you.
Yeah, thanks. A warm welcome once again to all the panelists and the students who have logged in into this meeting. See what, especially now talking to the students, what do you think that we are attempting over here? We are actually mimicking a typical industry scenario where customers are looking for technical solutions, and we have the teams, all of you form into teams, and then you get the opportunity to come out with solutions over here. And now the schedule of the hackathon is such that you can organize your teams into based on your skill sets or based on the subtopics that you wish to explore in deep. Understand the problem statements that are being forwarded to you, and then come together as a team and provide a solution at the end, which is of course we will look more and more on how viable it is, how deep you have thought about it, and how much you have tried to think out of the box. Further, we will also look at your communication skills, because communication is the key ingredient in a successful career. So this also, you get a chance or an opportunity here to express this aspect of yourself. So all in all, instead of a 1 hour interview or a 45 minutes interview, we look, you also get a chance to interact with us and understand our product areas and the content of work. Also, we also get a good time to understand you, how you think, and together we come out at the hackathon successful, and then we go on into internships and then possible employment with Bosch. So this is the inspiration, that everybody gets a fair chance with each other, and we make a well-informed decision at the end of it. So once again, all the best to the students. Please use this bootcamp, which is like a foundation for this entire activity for you. You can use this to orient yourself with the content and understand how deep or where you have to explore further. Okay, thank you and all the best once again. Yeah. Thanks, Ramaya.
Thanks a lot, Sajid.
Yeah.
Next, we have Abhishek, who would be briefing about the event. So yeah, over to you, Abhishek.
Yep. Thank you, Amaya. You can see my screen, right?
Yes, we can see your screen.
Okay, I'll just put it to presentation. Yep. Fine, right? Okay.
You can swap the view.
Yep. Okay. Yep. Let's see. Okay. Thank you.
Done.
So, good morning, one and all. Today I'll be briefing about the event structure for the day. Once my briefing is over, we'll be moving on to a 40-minute session by Mr. Patil Prashant, Head of COE Electrification, Bosch, on the topic Know Your Problem Statement and an Introduction to Electric Vehicles. Once the session is over, we'll be having a 15-minute break. And once we are back from the break, we'll have a session on design and control of an e-machine by Mr. Vikas P, subject expert in electric machines. Followed by that, we'll have a 45-minute session by Dr. Jeevanand S on the topic AI and ML in electric vehicles. Followed by that, we'll have a session on blockchain for electric vehicles by Mr. Patil Prashant, which will be a 15-minute session. Then you'll have a break, a 1 hour lunch break. And once you're back from the lunch break, we'll have a session on design and control of inverter by Dr. Subhash Joshi. It will be a 1 hour session. Then we'll have a session on design and control of DC-DC converter by Dr. Subhash Joshi itself. Then we'll be having a quick 15 minutes break. And once you're back, we'll have a session on design and control of onboard chargers by Mr. Shubham. Followed by that, we'll have a session on smart grid for Battery Electric Vehicles by Dr. B. Dastagiri Reddy. After that, we'll have a case study for EV product by Dr. Sadeep. And at the very end, we'll have a closing remarks by Dr. Vasanthi V. And I'd like to make some few announcements for the smooth conduct of the event. First of all, doubt clearing sessions there will be doubt clearing sessions at the end of each session. You can have your questions in the chat in between the sessions, and at the very end of each session, we'll moderate the same to the resource person. Second, we will not be answering any administrative questions or any questions related to the organizing of the event. For the same, we'll share a Google form via WhatsApp and email so that we'll respond to your queries as soon as possible. Then we'll be having a feedback form at the very end. Please fill the form so that we can improve and provide the necessary support for you. And also to the students, certificates will be given for this bootcamp in 2 weeks' time. But please note, only to those attending the sessions will receive the certificates. That's all. Thank you.
Thanks a lot, Abhishek. So with that, our inauguration ceremony is officially over, and at this point I'd like to thank Yusuf, Sharada and Shanoy for taking out your valuable time to join us and for sharing your wise insights. So thanks a lot, and yes, next we can move on to the problem statement, the much awaited session, which is a problem statement. So I call upon Mr. Prashant Padil. He's a group manager here at Bosch. So, and he is also leading the COE Center of Excellence for Electrification Topics. So yeah, over to you, Prashant.
Amay, it's a pleasure. Yeah. And I thank all the eminent speakers here. The stage you have set at a very high, yeah, so that it's very difficult for me to catch your pace, yeah. So it's an honor, friends, to have this knowledge sharing session to you. And there will be typically one question: why we should have a boot camp, yeah, for such an event. So, Amaya, before that, please acknowledge if you can see my screen.
Yes, we can see your Outlook.
No.
Okay. I think you can open the PPT and start presenting again.
How does it look?
Just a minute.
Under choose screen, you can choose PPT slideshow.
How is it now?
Yeah.
Yes.
Yeah, it's perfect. Okay, so keeping it in full screen.
Yep. Yeah.
Okay, good. So, friends, we will start with say why we need a bootcamp here. Yeah. So typically, this is an all-India workshop. Yeah. All in the hackathon, which is a slow-paced hackathon. So this, you might not have seen enough or many such initiatives in India. Yeah, we don't want to create a 1 or 2 day and just to check like how fast you can learn and execute. Yeah, rather we want to help you with the knowledge and equip you with the enough capability or competency to work on our problem statements, and we give you a speed time of say 6 months. Yeah. And we help you with all the necessary knowledge required for this thing, and then we test you, yeah, how you're using the knowledge, how you're applying to the problem statement, and how you're presenting. Yeah. So with me you can see Jason and team, so they are the winners in the first season. Yeah. So I'm proud to say that we have 2 of the associates who already filed patent, yeah, in Bosch in just 1 year. Yeah. So the whole objective of such initiative is to find this passionate pool who is really passionate to do something and give them a platform, yeah, irrespective of the college, whether you're from IIT or whether we are from a Tier 3 college, a private college, yeah. anywhere, if you are really skilled and if you are really passionate, we are there for you. Yeah. So we want to give this message, and I want to start with the problem statement. Definitely, you might have received, you might have gone through the screening, and it's like Yusuf was telling, it was 4,000 plus registrations. Yeah, and we never expected this reach, but and thanks for all the interest, and I'm proud to say that we have close to 1,700 students clearing our eligibility criteria. Yeah, it's 45 to 50%, and this is good. Yeah, so what we are expecting you from this particular hackathon. So as you know, we kicked off a little bit early, 24th May. You might have received the first flyer by April, yeah. And we are on 24th June with the bootcamp now. And we would be having one more level of screening, yeah. So this is typically to check like how much you have progressed. So we will be sending you a template of manuscript, yeah, like you apply for IEEE papers, and you have to meticulously put actual work done. Yeah, so there will be some evaluation from our side around September, and we will be finalizing close to 25 to 30 teams to the finals. The finals will be either virtual or physical, which we are discussing, and you will get an opportunity to present your solution to the expert panel which we fix, yeah, which includes IIT professors with our experts and including international engineers also, yeah. So this would be an allied panel, not just evaluating you, but rather guiding you what can be done with the problem statement or solution you created, yeah. And throughout this journey, 6 months, so today we have 6 to 8 speakers presenting on the topics. They will be along with you. Yeah. So any doubts, you can approach Dr. Sadeep, the Reliable Automotive Labs. They will be taking care of you. They will be helping you with the necessary questions. Yeah. So it's like not the bootcamp never ends here. You will have an opportunity to interact with the experts also, and we will be sharing you the necessary contact and the protocol. Yeah, it should not be like you should contact them continuously. They are busy people. Yeah, we have scientists today, we have professors today, we have industry leaders today. Yeah, so we have a set of protocols we will be sharing. But given that we are there to help you out, provided you are passionate and you really want to crack this. Yeah, coming back to the problem statement. Season 1, Season 2, we had one problem statement, that is digitally design your EV. Yeah, how to design the components from the vehicle, say how from the requirement, how you pick a vehicle, whether it is 2-wheeler or a 3-wheeler or a passenger car or a commercial vehicle. Then how you select the components, say what is the rating of motor, what is the rating of inverter, how is battery design, and you take all these components and fix it into a digital model and a mathematical model and show us like as simulate and show us like what is the result. Yeah, what was your expectation, where are you? Yeah, so this was the problem statement last 2 seasons. Now we received a lot of feedbacks from students from other branch, for example mechatronics, yeah, instrumentation, and who would want to explore a little bit deeper into their domain. Yeah, so we made a diverse problem statement this time. It's a 6 pillar, very simple. Yeah, we don't have a very sharp problem statement to give you a freedom. We have kept it very open. So I will explain one problem statement and touch upon other problem statements, yeah, at the surface level. So it would be like easier for you to for us to meet within the scheduled time. Yeah, further questions you have, you can always contact Jason and Amaya. We will be open to support you. Yeah, so the first thing is like, let us take the design and control of electric machine. The expectation is like you have to dimension a machine. For example, when I say dimension and dimension, you have to handpick a machine for a particular application. For example, if you want to design it for an electric car, say Maruti Alto, yeah, what is the size of the machine? Yeah, it can be very simple. For example, you can take the engine capacity and you say that this torque and speed I need to meet, hence I want this machine. Or it can be a complex. You can make a digital model, you design, you dimension the components. I will have a session coming up. I'll show you how to do this. Yeah, and you make a mathematical model and you see that yes, this is the torque and speed requirement and the power envelope of my machine. Yeah, then you handpick the machine. Then the next stage is you design this particular machine, and we are very pretty clear. We want a PMSM or BLDC. We don't want an induction machine here, yeah, or an advanced technology SRM machine, because we want to ensure that we want to keep a boundary here for you to explore. Yeah, as you know that permanent magnet machines are more popular in the electric field domain. So let us assume we are designing an PMSM machine. Yeah. So now you got the torque and speed requirement. Then the next level is you have to design the machine in some software. Yeah. Definitely there are many softwares available, or some analytic calculation also you can make. For example, you can you know the torque and speed of this machine. The next level is how to design this machine. Yeah. What I mean by design is that what is the machine has two parts: stator, rotor, and one controller. Yeah. So you keep your focus fully on stator and rotor, and you keep simulation for the controller. Yeah. So what is the length of the stator? These are mathematical calculation. You can just do with the Excel sheet and try it in some software. Yeah. Definitely your colleges will be having the software. Otherwise, we have requested the consultant today who is taking the workshop to help you with a software trial license. Yeah. So you can design the stator, number of turns, and the slot fit factor and type of magnet into the rotor. Yeah. And you come up with an physical dimension of all these components. Yeah. So that this fits to the requirements. Additionally, to validate this thing, you can do two analysis. One is an electromagnetic analysis to ensure that the flux is proper in the air gap. Yeah. You are not demagnetizing the magnet. Yeah. Or you can additionally you can also do that, say what they call it as stall current. Yeah. When the rotor is zero at a zero speed, you pull in maximum current and you test the magnet for this case. Yeah. These are advanced topics. So I mean to say that you can have a simple design, yeah, with some software, and justify why you picked this motor and how you designed it, and also explain about the characteristics. These are the one example. Also, you can go for a complex.
Prashant, we can't hear you right now. Could you type in the chat? We can't hear you. Hello? Oh, someone's muted.
I hope this is now we are audible.
Yes.
Can you acknowledge someone? Yeah.
Yes.
So we were at electric machine. Yeah. So you can have a complex design. The complex design means you take the design parameters, input, say torque, speed, and power, and you take some software like ANSYS Maxwell, and then you do an parameterization or optimization, and you exactly come to the best design possible. Yeah, be it the number of turns, or be it the size of the stack, or be it the thickness of the lamination, or be it the air gap. I think you can put all practical cases. For example, the minimum possible air gap can be 0.5 millimeter up to 0.3 millimeter. Then you can tell, like, because the machining requires this requirement, so we fix the air gap at this level. Yeah. Then you can select a very practical magnet which is available from the from the market. Yeah, say an NDFEB with an the residual flux value of say 1.5 Tesla, whatever. Then you make a proper machine design, and you present us the simulation results of electromagnetism, and you can even do a transient analysis. Yeah, what is the starting torque, what is the maximum the ripple created while starting this thing. You can go to a very detailed level, so that even if you finish this hackathon, you can go and make your prototype, yeah, and present it as your final project. Yeah. So these are the two extremes you can do with one problem statement of machine. Similarly, you can go to design of inverter and design the power module. Yeah, have a simulation model. For example, have an intelligent model to decide on what is the switching conduction loss, what type of switches you are using. Have a proper justification. Yeah, and if possible, definitely make a proof of concept. Yeah, I'm not asking you to make an inverter for 100 kilowatt. Yeah, make a small applications and come up with a hardware. Yeah, if possible, even if there is no hardware, come up with a very solid model. Yeah, definitely we will be giving you credits or marks based on the depth of engineering you have done. Yeah, and also what novelty you are bringing. Yeah, beyond what you learned from the college. Yeah, and there is no right and wrong. Okay, maybe your inverter will be efficient only 60%, while market you can see 96%. It's okay, but you design it and show it. Yeah, and you have your justification and you understand why it is only 60%. That is sufficient. Yeah, then the next thing can be a DC-DC converter, a buck converter, or a buck boost converter with a proper justification. DC-DC converters, as is simple, it's relatively simpler. Yeah, so a good team would be someone who presents a hardware here. Yeah, so you have your backend calculation. For example, why you picked a particular converter topology and what application you are using. Yeah, and the next thing is like where your edge is coming, novelty is coming. Yeah, and also what are the functionality and how you fabricated it. Yeah, for example, how you design the PCB, how you design the transformer, whatever. Yeah, so have a proper justification and what basic simulation you have done, maybe a Monte Carlo simulation. Yeah, so follow a typical design methodology for a DC-DC converter, because it's relatively easy to make. Yeah, so we know that the problem statements are very diverse. Yeah, we want to visualize you as an entrepreneur, how you pick this and how you come up with the solution. Yeah, then the fourth thing can be onboard charger. In electric vehicle you will have onboard charger and offboard charger. Yeah, so charger sitting outside the vehicle or inside the vehicle. Yeah, the charger functionality typically how to charge a DC battery. Yeah, from a home supply or a DC supply. Yeah, so onboard charger is again one more converter. Yeah, you can we expect a POC. Yeah, we expect a proper design methodology, and to extend you can present a POC, we are okay. Yeah, and anywhere you struck up with some practical difficulties, we will have touch points to help you out. Yeah, we won't be guiding you to help, like for example, pick this IGPT because so and so, but we'll be addressing the blockers what you have and giving you some recommendations. Yeah, don't expect we sit with you and do the coding and the simulation. No, that is not the intention. Yeah. Then the fifth pillar is AI, ML, and or blockchain for EV. Yeah. So you can take a simple application. Yeah. Say prediction algorithm. Yeah. How to predict the electric range of a vehicle. Yeah. And you come up with an app or something. Yeah, for example, and put the algorithm somewhere and show a live demonstration. Yeah, you can use any available embedded system boards. Yeah, be it Mix. Yeah, whatever boards, open source boards you can use, and you create something unique. Yeah, so we judge the digital topics based on impact it can create. Yeah. It can be a simple topic, but to what extent it can impact an EV. And we are very particular. It should not be something like just an app. Yeah. Like for some application, we want it connected to electric vehicle, because this is a hackathon which is running for EV topics. Yeah. And the fifth one is the static application, the smart grid. Yeah. You can put the concepts like a bidirectional charger design. Yeah. And an algorithm to monitor this charging. You can bring the digital perspectives also inside the smart grid. Yeah, and pick a solid problem statement. For example, how you enable, how you say, make a transaction system when you do the vehicle to grid charging. Yeah, assuming that the utility is supporting this, and how you enable this particular protocol. Yeah, or how you design a particular algorithm and put inside a hardware and show a demonstration. Yeah, so this is a static application which you always can do. And always one request is that be very authentic. Yeah, whatever you are doing, just show. Don't take anything from internet or something and just to support your claim, because we have a very systematic process to identify whether something is copied or not. Yeah, we have seen many cases which we couldn't entertain further. Yeah, so once more to repeat, we will be like evaluating you on the depth of engineering done, yeah, for this problem statement, and authenticity, how authentic you are you using anything from the past work, if so, what is the justification you are transparently telling, yeah, and also how you are presenting the idea. It's okay that you have a great idea and you made a great prototype, yeah, but we need to understand to what extent you're done. So the communication aspect and how you are presenting the idea, how systematically you're doing this thing, this is something which we are expecting from you. Yeah. So believe me, the top 3 teams for last 2 seasons are outstanding in three pillars. Yeah. So in the sense they didn't make a big product and all, but whatever they made, they are very authentic. Yeah, and they have a pure justification why they picked a particular topic, why they picked a particular machine. Yeah, and they have supporting simulations and pure justification how they did it. Yeah. So friends, this is your forum. Yeah, you through this you are getting into the niche area of research and development happening in India. Yeah, and I'm proud to say Bosch is leading the electrification, yeah, for future, and this is your window to explore and get along with us. Yeah, and yeah, join and just let's change the future of mobility how we want. Yeah, so this is the first step, friends. Yeah, and I also want to tell you that where are you now? Yeah, so Amaya, I'm in the second slide. Can you see this?
Yes, we can see you.
Yeah. So friends, we have 4,000 plus registrations. Yeah, 4,000 plus. Okay, and like so it's like whatever you can see, 800 plus 120 plus 10 into 4. Yeah, and last year we had a problem. We had only reached till South India, maybe a little bit on the west side, West India. But now we have good representation. Definitely South is we have a great representation, but other places also we have excellent teams participating. Yeah, so it's truly an all India reach. We have at least one team from almost every state. Yeah, and this is we are really proud of. And when you are competing this, one point you need to consider is that you are competing with the best of minds in India. Yeah, at your age or academic level. So put your best. Yeah, and I'm sure that you will come up with a great solution. And this make like Professor Sharada was telling, yeah, you can even take this and make a startup. We are always supporting such initiatives. Yeah, so take it as an opportunity. And why we kept this hackathon this phrase is that you can take the topic, expand it to your personal project also. Yeah, we have many of the students last year who expanded this thing and made their project. Yeah, so this is overall a total gain for you, and all the best for this. Yeah. Having said that, I will just show you basics of EV, because there was one request to include some EV topics in the first discussion. Yeah.
Thank you, Prashant, for that session on knowing the problem statement and the outline on the hackathon. Yes, now we will have an introduction to EV. Yeah.
Guys, you can see my screen?
Yeah, Prashant. Yes.
So, see, the electric vehicle, the evolution is a story, yeah, just like any Hollywood movie, yeah. It just started not like a right away you pick a battery, you pick a motor, you make an electric vehicle, nothing like that, yeah. So always, why this is required. There are social issues, yeah. The pollutions are increasing day by day. And the pollution norms or for the automotive has been expanding like anything. You don't have a BS5 stage in India, Bharat stage 5, yeah. We expanded from BS4 to BS6, yeah. We skipped one stage, which means that the adaptation to help a sustainable future is very much required, and electric vehicle is most accepted solution in mobility. Definitely there are other solutions like fuel cells, hydrogen, yeah, and the most practical is electric vehicle. The evolution started from an engine, yeah. So you want to downsize an engine and start with a small motor, yeah. So do you downsize this engine, you say 100 kilowatt, you put a small motor, then you make a combination, say you replaced a 100 kilowatt engine with a 100 kilowatt 80 kilowatt engine and 20 kilowatt motor, yeah. That is called a mild hybrid. So it doesn't have an electric mobility, it cannot run on electric motor alone, yeah. So it is something which supports, adds torque to engine, yeah, and supports the engine, so that engine is always at 80 kilowatt, and the pollution will be equivalent to that speed. So you keep the engine always at its efficiency point and take the rest of the torque from motor, yeah. So it is a mild hybrid because it's just supports the engine, yeah. And also it has another feature called recuperation. Whenever you brake, it can charge the battery. That's why in a traction or an electric vehicle, we never call it as an electric motor. We always call it as an electric machine because it can operate as a motor and a generator equally, yeah. The next evolution is a strong hybrid. So then people started thinking, okay, 100 kilowatt, why can't you make, and rather than 80-20 combination, why can't you make 50-50, yeah, so that you share 50% your load. Let us assume it can range from 30 to 100 kilowatt, yeah. So if for a 100 kilowatt vehicle, 50 plus 50 kilowatt, yeah. So advantage is that it will have an electric range, yeah. Mechanically, how it looks like, it will be having a clutch between the engine and the motor. You can disengage the clutch, yeah, and you can run the motor as such, and just switch off the engine, yeah. So you don't pollute the environment and you are getting a good mileage, yeah. That is strong hybrid, yeah. Then people started thinking like, okay, if this happens, why where I will charge my battery, yeah. Imagine that I don't have a recuperation of the scale to charge a battery full, and then how would I do this, yeah. Then they put a charger, yeah. Then they put an off-grid charger, like you have a charger externally, then they put it inside, yeah. So you can charge the vehicle. That's an additional feature. So then when people see that they can charge the vehicle, then they expanded the electric range, yeah, more than that. And you can see that throughout the story, the engine size is getting smaller and the pollution is getting better. Actually, we are not at all polluting, yeah. And finally, so finally we evolved to the electric vehicle, yeah. We took off the engine completely. Then there was a case when you drive to, say, forest or some ghats area where you cannot get the charging facility, and but you still need to have an electric vehicle, yeah. Then what is a way you can charge this vehicle? So one way is like keep a small engine somewhere, yeah, and just charge the battery as running as a generator, yeah, and use this battery to drive the electric vehicle or the traction motor. So that is called range extender. So it's a different evolved concept of hybrid vehicle, yeah, or a little bit close to electric vehicle. Then the final one is that you take out the engine, throw it out, yeah. You make an electric traction completely, and it can go up to 500 kilowatt. 300 kilowatt is something old. We can go beyond that, yeah. And how it looks like. So it's purely simple. Okay, electrification or electric vehicle doesn't have a, say, very complex architecture. Yeah, it's simple in a way that this can create a lot of innovations because it's pretty simple. Most of the people can get into this topic and change something. So the typical basic architecture consists of a battery, and some power conditioning device. Yeah. Because the motor typically has a permanent magnets, as I mentioned. Yeah. So to convert a DC battery, battery is always DC. Yeah. To say an AC machine. So PMSM is an AC machine. Yeah. And we need to have as a DC to AC converter, typically an inverter. And we use three-phase inverter typically for doing this thing for obvious advantages of getting maximum power, yeah, out of a particular rating. And typically the technology has evolved beyond IGBTs and MOSFET now, and the current inverters can reach up to 98% efficiency. Yeah. So the emission is typically PMSM, yeah, BLDC for some application, but PMSM is the most accepted solution because it is very compact. Yeah, that is the torque per volume is very high, and based on only negative part is the magnets actually, because negative magnet is always positive and negative. Positive in the sense it packs lot of energy in the small space. Yeah, because it reduces the rotor. So rotating part is typically a magnet. Yeah, so then it reduces the need of electromagnetism there, the winding type there, and it can be a small size and give that much power. The negative part is like temperatures are very sensitive to very high temperature. Yeah, I mean magnets are very sensitive to very high temperature. For example, if you touch a temperature about 180 degrees, the magnet can go to a different operating zone. Yeah, which can be something called derating, we call it. Yeah, because the performance reduces, and magnet, if you continue that state, it dies typically, which means that you are completely moving out of regular operation. Yeah, so that is one disadvantage. How we make and enable that this is not happening is by properly designing the control system for that. Yeah. And then the next thing is you will have a single geared transmission in this particular topology. Unlike engines, yeah, you might have seen engines going till a maximum of 6,000 RPM, 7,000 RPM. Yeah, motors can be designed up to 20,000 RPM. Yeah, which means that we can have all the speed and torque operating points, I would say. Yeah, when you take a vehicle, you are literally creating operating points through your drive cycle. Yeah, drive cycle is nothing but velocity versus time if you plot. Yeah, so all these operating points can be covered by a machine which is properly designed for the application. Yeah, so you don't need a multi-gear here. You can meet all the requirements with one gear. Yeah, while it's an engine, you need some 4 to 5 gears because its operating speed is only 6,000 RPM. And another beautiful factor with an electric motor is like it can always be started at maximum torque at 0 RPM. Yeah. So this is enabled with an algorithm called field-oriented control, where you know it, SVPWM based algorithm, which you have studied in your third year classes. Yeah. And then the conventional part of differential to wheel. Yeah, so the energy flow for motoric operation is from the battery to inverter to emission to the transmission and to the wheels. Yeah, while it is braking, it is adverse. Yeah, it is reverse in fact. And you should also know that whenever there is braking, always it's not always electric machine will work as a generator and charge the battery. Imagine the case where you have a battery which can say which is 100% charge, where you dump all this charge when it is braking. Yeah, so always in an electric vehicle you have two types of braking: mechanical braking and electric braking. So the split between these two is decided by a control algorithm, which it takes care of a lot of factors like the state of battery and the speed at which the vehicle is going. Yeah, so so whenever you are braking, it is not correct that you're always charging the battery. Yeah, there are many cases, and we don't have enough scope to explain this in this current, say, 8 minutes left here. So this is the overall architecture of a single speed and most accepted configuration of an electric vehicle. Imagine the case of an 4x4. This doesn't work. You need to have control on 4 wheels. Yeah. So you put an axle with the same configuration. The beauty of this configuration is that you need to decide how much torque I need to give from my rear axle, then from my front axle. Yeah, under such cases you have to always employ a vehicle control unit or a master control unit who takes a decision, who understands all the situations happening in the vehicle, say how much torque driver is asking and what is the state of my machine battery state. I mean, my machine is okay to give complete torque, my battery is fully charged, it can give complete torque, if not, how much torque. So it listens to everyone, and the master controller take a decision. Yes, axle A, the front axle you give say 30% torque, rear axle you would say 70% torque. And this is a beautiful field. You know how many innovations you can make in this field. No? You can bring your own control theory and control algorithm inside this master controller and see how it is getting implemented in a virtual model. You can do it right away in your campus. You know, you take a vehicle model, take MATLAB based vehicle model, hundreds of models available, play around this with this algorithm, come up with a configuration. Yeah. So 4x4 always enables this capability. And point to note, there is only one battery. You cannot charge and discharge a battery simultaneously. The basic physics. Yeah. Given that when we go for an application of a commercial vehicle, say a lorry, a truck, in our language, yeah, and a bus, we cannot meet the torque required for this, but maybe with one machine, because these are huge, yeah, mass wise, and torque required is pretty huge, yeah. So you need a multiplier under such cases. So one machine cannot give, you cannot put n number of machines, because it is it's a poor configuration, you know. So you either need to put a multiplier, which in mechanical terms means a gear, yeah, which multiplies the torque, yeah, and ensures that you are getting the right torque at right required point. So you have a multi-gear configuration under such applications, yeah. I'm not deep diving, it's only variation. Then you can mix everything. You can have a 4x4, a multi-gear configuration. You will get the best out of torque. You put it in a performance vehicle, and you get best out of everything. Then the fourth one is hub motors, where you don't have a transmission. You directly connect the motor to wheels. Yeah, the tricky part is that the complete configuration of electric machine is different. So when you are designing a machine for hub motor application, it should not be same thing what you design in the first topology. Yeah, because this machine speed should fit to the vehicle speed. Yeah, so if you design 20,000 RPM machine and keep it there, the vehicle's wheel speed is 20,000 RPM. Yeah, you convert it into velocity by multiplying with a radius or whatever. Yeah, but it's not what required. Yeah, it doesn't fit the requirement. So you need to have a machine for such applications which caters to the wheel speed. Yeah, at the same time it should be enabling higher torque, because you don't have a transmission, so it need to enable that multiplication factor here. Yeah, so this is a tricky configuration topology, and you can see some vehicles in the market also. Yeah, so what I mean to say that electric vehicle and the topology is basically the arrangement of these components is not just one or two. Yeah, you can create your own version, you create your own topology and come back and present this. Yeah, that's also fantastic as a good project. So we have seen that how we can what is electric vehicle typically, what is evolution story, and I will show you one application how you can build an EV. Yeah, so you can start with an use case. For example, you can find out 2 points in a Google map, yeah, A and B, and see the distance, and just drive through that part and can collect the velocity versus time profile. Yeah, you will get it in some MATLAB applications. There are many apps for that. Yeah, and you see for that application, imagine 365 days you are driving this profile once. Yeah, then you create a vehicle for this application. So you collect the use cases in the first step. You don't need to worry about lifetime and all. These are OEM terms we makers do. Yeah, for academic purpose you can ignore. So you create your drive cycle. Then there are a lot of vehicles available with a set of parameters. Yeah, or you design your own parameters. Yeah, parameters I mean a lot of physical parameters like frontal area, coefficient of drag, which you will come to know when you explore how to design a vehicle or dimension a vehicle. Then once the vehicle is clear, you pick a proper topology from whatever I shown. Yeah, which fits the application. For example, if it's a bus, you need to go for a multi-gear. You need to see whether it is multi-gear application, and what is the DC voltage required. Yeah, your 48 volt may not be a good solution for an SUV. Yeah, why? Because its power is high. If your voltage is lower, you will have to design a machine to which can withstand very high current, which is not good. Yeah, it will be big windings and the machine would be very big. Yeah, then it doesn't fit the purpose. So find the voltage which is fitting your purpose, and find the optimum gear ratio, which if you're taking an topology with the gear, and normalize the behavior, the torque, like how much you want maximum, and you confirm that part from here at the powertrain. Next level, once the powertrain is fixed, powertrain I mean the topology is fixed, see which is my mission. Is it a PMSM, or I want to go with an induction machine? Then what is the control strategy for it? Yeah, and so once you design, you enter inside the machine how I will design this machine. Yeah, so you have to pick the windings, other things like the stator, the type of material you use for this winding, and what is the cooling mechanism for this. Yeah, then you come to a subtopic level. Yeah, so this is typically a requirement breakdown from what you want to design and to what detail level you can do this. Yeah. So one case study how we do in industry. You may be using this thing or may not be, but this is one good mechanism for you to help understand how to design a vehicle. And I also want to tell that the total forces acting on the wheels is just a four basic whatever we studied in 8th, 9th standard. Yeah. So once you have all the total forces acting on a wheels for a particular drive cycle, this is not a static point. It's always a velocity versus time profile. Yeah. So how you dimension it properly? Yeah. So you get all the forces acting on a particular wheels from a velocity versus time profile. Yeah, with a basic physics, and then you get the force. Power is always force times the velocity. Yeah. For a drive cycle, it is always the integration. Yeah. And so you get the power at the wheels. Then you add all the losses, say the transmission losses, then the electric motor losses, then the inverter losses and the battery losses. You can approximate a particular efficiency and add the losses, or you can design the component and add the losses. When you add all the losses, you will get the maximum rating of the battery required to meet your demand. So literally what you are doing is that you are running through this complete use case. So here you have a use case, a drive cycle defined, and to here you pick the parameters and keep it in that four equations which I have shown, and you get all the forces required, yeah, for the wheels. Then in the next stage, you add the transmission losses because we are following from the wheel to the battery. Yeah. Then you add the machine losses, then the inverter losses, and finally you get the complete dimension of a battery. Yeah. So this is in simple terms how you handpick the size of the machine or inverter or battery. You can do academically. Yeah. While coming to industry, it's a different story. We have to consider a lot of cases like what is the cost of the component. Yeah. And what is the efficiency which we want to meet? What is the temperature behavior? Yeah. And where to position the component? A lot of things will come. But for academic purpose, you just ignore that. So you just understand everything is basics. So this is the thumb rule. If you can break a problem to basic SI units, say mass, yeah, say velocity, distance, and you can explain everything in terms of this physics, yeah, be it current or charge or whatever, then you got the name. Yeah. So this is the way to build your project. So I have shown you a small demonstration how it can be done, and I think I overshooted 3 minutes, but I am sure that I am able to convey you that problem statement and a typical flow. You can approach the problem statement along with what you do, what is electric vehicle, and a basic topology with a small basic calculation. The slides will be shared to you. Any questions means you can always approach me later. Amaya and Jason would be helping you. Yeah.
Yep. Thanks a lot, Prashant, for your session. So next we'll take a quick break. Right now we will take a break for 5 minutes. So we'll reconvene at 10:17 a.m. Is that okay? So yes, you can all grab some snacks, drink some water, and we'll be back after 5 minutes for our first session of the day, which is Design and Control of E-Machine by Mr. Vikas B. All right then, see you. Hi everyone. So we'll address a few questions in the meantime. We have received one question. Will we receive presentations post meeting? Yes, we will be sending you all the presentations later, but we wouldn't be sending you the recorded session. We will resume in a few minutes. Over to you, Praveen. I can't hear you. Oh.
No, I hope all of you guys are back. So we'll be shortly starting the session. No? Let's start. To start off with the technical sessions for today, we have Mr. Vikas on the topic of design and control of e-machines. So he's a very passionate electromagnetic design engineer, having around 10 years of work experience working in the motor industry across home applications and EV applications. He is currently the lead designer at Matter, startup focusing on creating futuristic EV platforms and energy storage solutions. So, Mr. Vikas, are you there?
Hello.
Hello, Mr. Vikas.
Hello.
Yeah. Thanks for the intro.
Session.
Yeah. So my screen is visible, I guess, to everyone.
Yes.
Yes. Sure.
Okay, student. Let's start with the introduction. So basically, what happened in our e-mobility? If we are talking about the e-mobility traction kind of application, so we are thinking about motor is the key part, or we can say the main propulsion force generating unit. Without any motor or without any, we can say, the engine, we can't we can't think for the mobility. Even though it's maybe e-mobility or maybe some IC engine, we can say. So let's start from the boundary condition first. before jumping to design and development of motor and controllers, before that we have to understand the boundaries where we have to hit.
Because will you be able to turn on your cameras so we can see you?
I have strength issues, signal issue here. If I on, it will be a little bit.
Okay, it's fine.
Yeah.
Okay, it's fine. Yeah. Please continue here.
Yeah. Okay. So when we thinking about the e-mobility and kind of application, so basically we have to hit our boundaries first. So motor design or any controller design requirement comes from the basic point which we'll discuss in this presentation. Okay, so you already, I guess you have an idea, you all about, familiar with this kind of architectures of the EV motors or EV vehicle, we can say. So this is kind of a hybrid vehicle where we can generate the propulsion force by using IC engine and electric motor both. So it is one of the best, we can say, the propulsion system. Right now we can rely on it, even though we are facing issue with some battery, we can say the drainage, or even though battery charging, we can survive for long with this kind of system. So basically we go to the point. If we try to design electric motor or controller, we have to understand the traction force which will require to overcome, which will overcome by motor output. Suppose if any vehicle, suppose this is a vehicle, if I want to drive, if I want to move from one place to another place, so number of forces which will require, which will be come in a picture, and for the same we require to design a motor to overcome the forces. Suppose if I drive the vehicle, so acceleration force, aerodynamic drag or aerodynamic force, rolling resistance, clamping force, these are the four major forces will oppose the motion of your vehicle, or it will create the resistance to move forward from your vehicle. So basically, if I say the acceleration is mostly dealing with your mass and your acceleration of your vehicle. If from 0 to 60, how much time it will take? Basically, we are saying 4 seconds to 6 seconds. We are currently in trend, we are hearing that our vehicle is so good, from 0 to 100 it can achieve in 8 seconds, 6 seconds, 4 seconds. So it will basically show the crushing speed, or we can say the power of that vehicle. It is the parameter which is come under the performance category. If suppose someone vehicle goes to 0 to 100, 0 to 200 within less time, that means it is very powerful vehicle and it will crush that much of boundary easily. But in case of IC engine, they are designing high power engine, high capacity engine, so it will work. But in our electric motor, we have advantages by using less, we can say the rating motor, less power motor, we can easily crush. Because I'll explain you when I'll go to the characteristics of our motor. I'll explain how we can overcome this effect. So I guess you all aware about the boundaries or the requirements of our traction vehicle. So fourth thing I am again repeating. First is your acceleration force. When from 0 to 60, 0 to 100, you want to propel your vehicle, you want to go fast, then it required one power, that is our design boundary. One of design boundary. Then if I say aerodynamic drag, when your vehicle is moving forward direction or backward direction, some air resistance will come in a picture. Definitely air will push you back sometime. So that is the one opposing or resistance is come in a picture. So that is second force which is opposed to you. Third one is a rolling resistance. When you are moving or when you are traveling, or when your vehicle come in contact with any surface, maybe it would be concrete road, it may be pave road, it will be a smooth road. So some friction would be generated in between your tires and your road. So it will also the force which will resist the motion. Fourth one is a clamping force. it will come sometime when you are moving, or when you try to move on wheel or any climbing portion. So at that condition, the force will come in picture. So these four forces or force resistance you have to overcome by using by design consideration in our motor. You have to overcome these forces by motor output. That is the main concern. And if once motor is there, so definitely control will come in a picture. So what happens when you have to derive your motor requirement? Suppose if I want to go from 0 to 100 in a short interval of time. So because of that short interval of time, your motor will draw more current. So definitely your inverter is capable for to deliver that current. And inverter, how he can, because inverter is not an isolated part, he is in series with the battery. He is wraps, or he just absorb current from the battery and deliver to the motor requirement. So inverter is bilateral, we can say. He is dealing with both the control component, like a motor and like a battery. So let's go ahead. So I'll come with the basic design later, but before that I'll introduce you the motor types and their details. So these are the basic types, or it is general motors which is available in market. Even though you heard before that induction motor, BLDC motor, AC synchronous, brush motor, SRM, linear motor, stepper motor. Now these are the very basic type. Even though if we think about axial motor, radial motor, now transfer flux machines are using in current scenario in some time. So these are the basic we learned before, so I'm not spending so much time here. But why I'm showing this, these are the options in front of you, and you have to choose your motor according to your requirement. So basically, if you design the small capacity motor, basically if you want to design motor for the e-cycle application, or the application where your speed requirement or the traction forces are less, to overcome this, you want to go for the high efficiency motor in less, we can say the pouch, or you can say the less dimension. So definitely BLDC, PMSM will be the optimum solution for the same. If you want to go for the basic strategy, so here I'm just telling why controls play the most important role when you are designing for the e-cycle or any small electric propulsion machine, where the precise control is not required, because even though we don't have that much of high speed, so in that particular application you use BLDC motor with simple controls. You can easily control it without, and even though it directly reflect or proportional to the cost of your product. And if you go for the little bit medium or higher rating machine, so you should go for PMSM kind of machine. So it will give the optimum efficiency, optimum controls, and we can say the performance as well for a long. But definitely you have to, it will directly land up with the performance is directly correlated with the cost, you can say approximately. And if I say about the induction motor, so induction motor is also the good options nowadays, because the induction motor, we can say the benefits. Is it easy to manufacture? It is cheaper in cost, and even though we are built, or we are designing the motor for a long, from maybe I am not say about last 3 or last 10 decade or more than that, we are trying to use the same motor for the traction application. So nowadays we are for a higher, here we are required higher performance at a higher kilowatt rates, at higher propulsion power. So we use induction motor, because nowadays we already develop controls for the same. So these are the characteristics of induction motor, where you can easily you understand it. I'm not spending more of time because it is easy to understand everyone. Their top speed characteristics is easy, and we have to control this anti characteristics by controlling the driving techniques and improving the driving technology in topology. So now we go for the BLDC or PMSM motor very fast. So BLDC motor having why we are choosing higher efficiency or higher, we can say, the BLDC motor performance, because it will give you the wild top speed range. I'll go to the characteristics. So okay, you can see this is the PMSM or BLDC motor characteristics. Mostly what happens, our IC engine having a limitation, we are not getting peak torque or max torque at a 0 or minimum RPM. So for that we have to incorporate, or we have to add gear in between wheel and our traction motor. So we use BLDC or PMI, some kind of motor which will give the high torque, high speed, even though at a minimum RPM. So we have to overcome the forces. I already discussed you during acceleration, when we are moving vehicle from the zero position, or when we start a vehicle from 0 to 100%. At that time, we require acceleration force. To overcome the acceleration force, our BLDC PMSM motor characteristics is capable to deliver. And for the same, we prefer to go with the BLDC or PMSM kind of motor. So I already told you why we are try to correlate our EV with the PMSM or BLDC, because all the forces which is try to overcome in our traction, that is acceleration, aerodynamics, rolling and climbing, which will be done by our BLDC and PMSM motor characteristics. Nowadays, even though in induction, we have to go for the little bit complex control techniques where we can easily meet the requirement. So now before jumping to the construction, I'll go to the first slide where I'll explain you the design process and procedure of the PMSM motor. Okay, so now this is the, we can say, the design process of any motor. You can say initially you have to think about their characteristics. I already discussed earlier. If you have the acceleration, aerodynamics, rolling, resistance, climbing force, from there these are the boundary conditions where you can derive your torque and speed requirements. Once it is freeze, you have to go for the basic construction or motor design. Suppose you have to go for the higher torque, lower speed machine, or lower torque, high speed machine. You have to, these are the characteristics, or these are the boundary limits comes from your traction force which is required to overcome your needs. Suppose if you are going for the if once it is confirmed, then you can select number of slot and pole configuration. Definitely various factors is important to while selecting the poles and slot, but I'll tell you this one example. Suppose if you want to develop a motor for high torque application and low speed, so definitely your poles and would be more, and slow, your poles will be higher, so it will give the optimum, or you can say the max torque with the same, we can say, the rotor volume or the stator volume. So that is the basic things I am taking. But even though we have to consider or we have to think lot of measures behind this. Suppose if I go for the high power density motor, currently we are using neodymium magnets, that is rare earth magnets, and rare earth magnets are costlier nowadays and the prices are going high. So even in rare earth magnet, we have an option like ferrites or ferrite kind of things. Even though in India is also in some developing some ferrite kinds of magnet at cheaper rate, but if you go for the ferrite kind of magnet, then definitely we are save the cost. But other factor we have to think, like our motor will not design for the higher power density. it is required in EV, because in EV we have a space concern, we have to weight concern. If we choose ferrite magnet, suppose I'll give the example, then definitely my weight of vehicle will increase, because anyhow power density will be less, so weight of vehicle will be high. If my weight is high, then definitely the propulsion force which will require to go from one place to, or propel the vehicle from one place to another place, it will increase. So definitely I save the cost as I compromise somewhere, but anyhow it will directly impact on my motor performance and my performance of my vehicle. If I say it directly correlate with the range of the vehicle. Means suppose initially with high power density my vehicle goes up to X kilometer. So if I go with a less power density motor, so I'll land up with the X minus 2 or X minus Y, we can say the kmph. So we have to think about those things as well. We have to think or we have to consider those portion in our mind when we are designing the motor. So cooling and the strategy, or finalization is also most important things in designing of motor as well. So if suppose once you are defining your boundary, then you are defining your cooling, your overall dimension, your materials, everything you define, then you can start the analytical, we can say you start the validating your design. Validating in the sense you have to choose your flux linkage, you have to select your flux density. So initially analytically you can calculate your tooth width and height of your stack, everything you can calculate. After that you can check it through the simulation. So I am now directly go to the simulation. Before that we have to select ampere turns which is required, which is try to overcome the electromagnetic force which is available with rotor. Then if and winding ampere turns is directly proportional to your copper losses. So if once you are defining your copper losses, or if you freeze your ampere turns, then it is going, you can move for the simulation, electromagnetic simulation. Once electromagnetic simulation is over, in electromagnetic simulation you have to make a note which point in which area you have to cross check your boundary limit, you have to cross check, you have to identify your requirements. Suppose most of the time if you go for, we are choosing good cooling system, good overall dimension, but it is not efficient, it will not efficiently overcome your requirement. Suppose if I go for the higher copper losses, my cooling system in such a way that it will extract the heat from the copper only. So it is also correlate with your border limits. If suppose if you are not extracting the heat in a good manner, or if it is not possible to extract heat from your system, then definitely it will impact on your performance as well. So after in electromagnetic simulation you have to cross check your ampere turn capacity and all. Once your electromagnetic simulation is over, then you can go for the next level. You have to check your you have to check your thermal boundaries of your motor. If you in thermal boundaries, if you meet all the requirements, suppose mostly you have to calculate your battery SOC, from how many times, means how long your battery will survive and how long your battery will work for to give that much of power to your motor. So you can go from one place to another place, or you can travel X distance. So if it is you have to consider those requirements coming from your driving cycle, or your any reference cycle which is required for to derive those or to identify those parameters. Suppose once your simulation of electromagnetic is over, the simulation of thermal is over, then you have to jump in the NVH kind of simulation. Suppose in EV, if your NVH is not good, so it will directly reflect to your the performance. How I can explain? Suppose your forces of stator and rotor and because of forces, there is some frequency will be generated in your stator stamping, and suppose the frequency of stator stamping and your housing will be matched or the same. So because of that, resonance will create, and because of resonance, your system or your motor will give the more vibration. It will more vibration and noise. If it will give the noise, then definitely it is an issue, but we can ignore. But if it gives the vibration, so definitely it will decrease the life of your motor. So you have to think about motor, and suppose in anywhere, suppose in case of electromagnetic simulation, thermal simulation, and anyway simulation, anywhere you have to stuck, or you have to hit your boundaries or your extreme limits, then you have to think, or you have to redesign or remodify your parameter. Maybe suppose your vibration is higher or frequency, so you have to increase your core back thickness, you have to change your materials as well, and you have to go ahead. So after the in-base simulation, you have to go for anyhow. After simulation, we can go for the prototyping, and after prototyping, we can go for the testing. So testing will be first is the performance test, first is the type test. That is a basic where we can measure the basic parameter of our motor. That is inductance, capacitor kind of things. Resistance, inductance, then insulation, and then we can go for the performance. After performance, we can go for the durability kind of testing. After durability and before durability, then go for the IP testing. So our motor is not only our design concept, or our boundary of designing is not limited up to the electromagnetic designing. We have to think about the electrical inputs coming from the controller and the output, that is a speed torque, which is a deliverable for our motor. But apart from that, the in-range impact, thermal impact, then your IP of your motor, everything should be considered while designing the motor. So okay, let's go for the next. So these are the various type of construction of stator. So if you can say first stator, that is the basically this is stator of the hub motor, which is used in e-bicycle, and it is the winding which is done over, that is a concentrated winding. The second one is a distributed winding, or we can say the ITM motor, inner runner motor stator is there. So you can say distributed winding. You can see here that winding is distributed. Third one is not important. Then we can go for the various type of construction of motor stator as well. Right now we have a facility. We have the our production. We can say the instrumentation we have. So we can go for the segmented kind of motor. Now I'll explain the importance of the segments or importance of the material selection. If we go for the higher grade of material, maybe various type of grade of electrical steels are available in market right now. So every steel having their own losses characteristics. Some steel give the less loss, some steel give the higher losses. If I say I explain the one grade, like this 50M350. So thickness of the every stamping. First I'll explain you our whole stator. It is not made up of a single block of EMS. It is made up of the number of laminations. Suppose I have a 100 mm stack. So if I use 0.5 mm thickness of single lamination, so I use 200 lamination to develop the single stack. And those stack would be those all the 200 lamination would be compiled, or we can say the put together using welding, using auto stitching, or using clipping kind of solution. We can hold it by using it. Sometimes by using bolting we can hold, but it is rarely you can see that. So if suppose your thickness of stamping going from 0.5 to 0.35, it is less only. So definitely in your current, before that you use 200 lamination for 100 length. If now you are considering 0.35, definitely it goes beyond 300, 250 or 300. So now number of stampings, we can say the number of stamping are increasing. Stamping are increasing, but definitely you are getting benefit in terms of the efficiency. If you go for the less thickness of your stamping, then you are getting higher efficiency because your iron losses will reduce. Similarly, in case of copper, I'm saying if you go for the higher gauge, higher area of your copper, then you are getting benefit in terms of your copper losses. Your copper losses would be repeat. So iron losses and copper losses, these two are the dominant factor in your motor efficiency. If you overcome or if you manage those factors, then you are getting benefits in terms of efficiency. No doubt, mechanical losses, hysteresis losses are also the part of the losses, but these are two are the dominant factors. Okay, so these are the various type of construction of your motor. First is induction motor. It is all three are the inner runner motor. Rotor is inside or rotating in, and if you go to the SPM motor, IPM. So I'll tell you the short SPM and IPM. So basically, what happens when we are designing the motor for the traction application? So definitely we try to deliver the more torque. More torque is here I'm talking about the reluctance torque. Suppose in case of SPM motor, we are not getting that much of reluctance torque, even though we are not benefited by the reluctance kind of torque in SPM. So in IPM motor, we can get a reluctance torque. Suppose if I give the same current, same input power to both the motor, and I'll get X torque from SPM motor and X plus Y. Maybe it may be 1%, 2%, 10%, depending on your ID and IQ current. I'll discuss later. So it would be beneficial for us to go for the IPM. So generally, why we are choosing the IPM? Because we are getting benefit of the reluctance torque. So now you can see here, Hellbatch is there. So basically what happened presently, we are now, because of the technology, we can change the orientation of the magnetic field in a single magnetic pole. Some would be the upward, some would be the downward, some would be left or right. As per our requirement, we can develop or we can ask for the magnet which will fulfill the requirement of our magnetic field path. So because of that, we are getting more. It will also help us in the efficiency kind of things, because our field orientation is in a single direction. If our field orientation is one direction, then definitely we are our ampere turn, or we can say the HE, which is required to push the force in a forward direction, will be the less only. So these are the common list of material we can use in our motor designing. If you say the stamping material, that is a carbon steel, stainless steel, currently SMC material is coming. So SMC having good, we can say the flux, we can say the good flux conductive capacity is there. We can in not a bi-direction only, in all three direction we can conduct the flux by using using SMC material. But they are having some own disadvantage. Means if I say about their cost is a more, we can say the dominant factor. And even though in production facility, currently in India, very few people who are manufacturing such kind of materials. So these are the limitation for this material. Otherwise, the silicon steel means electrical steel is commonly used for a long, and this is a good solution nowadays as well. If I say the dielectric material, motor is not made up of only the winding, steel and the magnet or the rare earth material. It is required some dielectric, or you can say the insulation material. That is the paper, that is the wedges, we can say. And even though sometimes we can use the epoxy kind of material, which can directly fill into the stator, in between stator and your slot. So because of that, it will not give the electrical only. It will not give you only the electrical isolation. It will give you the thermal conductivity of your motor as well. Suppose one motor you are going with the epoxy, and one which is without epoxy. You are only use normal paper, and even though you are not use any material in between winding and your stack, except the paper, Nomics paper or any kind of paper. So the conductivity, the heat conduction from your winding to stack to your housing to your ear, maybe the any heat extraction material. So epoxy will give you the best heat conductivity, and therefore it will easily extract heat from your motor to your winding, and it will deliver to the housing, and it will be the one of the efficiency improvement component in your motor. Even though it is a dielectric, or it is a non-conductive material, non-electrical conductive material, but it will beneficial for us to give maximum efficiency. So only magnet and only electric wire, or we can say the copper, is not a part of efficiency. Even though we have to consider all those material as well. Then go for the magnet wire. Mostly in EV, we are getting more efficiency, so we are definitely go for the copper. Otherwise, various good materials. So the composition of the materials, two different materials will be used in a magnet wire. And most of the thing we can sometime, if we go for the inverter operated motor, so people are thinking the enamel of the copper wire is important part, where we can think about. If we can go for the higher harmonics, if we are dealing with the higher harmonics which is coming from the controller, so definitely we have to think about the enamel, or we can say the insulation, which is covered with copper, covered by the copper. So it is required thing. If we go for the higher harmonics, if we are dealing with the higher harmonics, then we should think about the enamel of our copper. If we go for the good quality of enamel, maybe currently I'll say there is one wire grade is available market, which will with a higher thickness of enamel will be withstand the higher your hysteresis, or we can say the higher harmonics current. The heat generated because of the higher harmonics, it will mitigate. So only copper is not important, even though the insulation which is covered by the to the copper is important. Even though similarly, if I say the electrical steel, various type of coatings are available there. If you go for the good quality of coating, then definitely you are getting the efficiency improvement in it. So now I will jump to the IDIQ point. It is it is the heart of your control. So what happened? I told you, in IPM motor we are getting some additional torque, which is not getting in we can say in SPM motor. So here in IPM, internal permanent magnet synchronous motor, we are getting additional torque, which comes from their reluctance of your flux path of your rotor. Suppose and now what happens if we can say if we want to extract the reluctance torque from the motor, we have to give some input. Definitely, if you want something, then you have to give something. So there are as I'll just explain this simple control. There is you are saying that we are only see RYP3 currents are going or moving from controller to the motor, then from motor we are getting torque and speed. But what happens? Direct axis of your, I'll explain. I'll explain what is the direct axis and quadrature axis of your rotor. Suppose the axis which is perpendicular, it is a 90 degree of your magnet, which is a direct axis, and the axis from the axis between two magnet it is called the quadrature axis, or you can say the axis from the axis which is from 90 degree of your direct axis, electrical 90 degree. It is a quadrature axis. You can see here the different type of topologies or motors are there. They are having different ID, or you can say the direct and quadrature axis is there. So flux is flowing from the your north pole, we can say the direct axis, then moving into the air gap, then it is it is just coming back and insert into again in a magnet. So the path, the second magnet, and then come to the first magnet again. The path of flux is showing, it is the direct axis flux path. And similarly, the flux path which is coming from the quadrature axis, the arrow is showing here, it is called at the quadrature axis path. So now I guess quadrature axis and direct axis are clear to everyone. So now you are seeing if suppose reluctance in a flux in a direct axis, it is more, you can say in first, you can say radially magnetized magnet, because magnet is act as a air when you are talking about the reluctance, and quadrature axis reluctance is less in a first category. So the significance of the direct axis and quadrature axis reluctance is impacted in your field Wittering design. So now we'll discuss later. So now we go to the first graph again. So here, so what happens if you want to push, or you want to insert ID current forcefully? Forcefully means if you provide ID current, so your motor will start generating your reluctance torque. So nowadays what happens? Reluctance torque anyhow, when you are not, you should be aware about the magnitude of your ID current. Your ID current magnitude should be negative with respect to IQ. Then you are benefited with reluctance torque. If you give IQ and ID in the same, we can say the notation, or you can say that in the same direction means the magnitude, positive magnitude. Suppose ID having the positive and your ID and IQ both are the positive, then you are deficient by the torque. You are not getting reluctance torque. You will start losing your reluctance torque. Basically, ID, when you are injecting negative ID, then you are getting, or you are weakening your field of your magnet. So when you are weakening your magnet, you are getting, or you are deriving the reluctance from torque from it. So it should be you should be noted that ID should be negative with respect to IQ. Then you are getting reluctance torque. But if you want more and more reluctance torque, then you have to inject more and more ID. But we have some limitations. Suppose if you are injecting more ID current in your motor, so it will weaken your magnetic field of your magnet. Sometime it would be demagnetize your magnet. So we have to consider the boundary, or we have to stick with our arena where we have to stop our ID. Otherwise, if we are in a 3D mode, if you are injecting ID more and more, then we have to demagnetize our magnet. So we have to use ID up to that, where we can avoid demagnetization of our magnet. So these are the basic IDIQ component. This IDIQ is a rotor component. So basically what happens, R, Y, B, these are three phase current are the stator component. These are the rotating, you can say the component. By using Platt transformation, we are converting this A, B, C component into their two rotating components. That is called alpha, beta. If from alpha and beta, these are the rotating component of our stator. If I want to see the position of rotor from the stator, if I convert my two rotating component of my stator, so by using Platt transformation, I convert it alpha beta into IQ. ID, IQ are the rotor component, but we are controlling this rotor component from the stator. by using Clark and Park transformation. Again, by using inverse Clark and Park transformation, we are regulating the same things. This is the one FOC algorithm is there. Now I don't have time, so you can go and read. And if you have a question, please text me. Okay. We don't have time right now, so I'll go hurry. Limited time. Okay, so just I cover some testing, or you can say the measurement parameters. Not only motor designing and the electromagnetic designing simulation are the we can say the key parameter of your design success, or your design you can say the landmark. So basically you have to stick with your dimension, because if you play with your air gap in high power density machine, play means if your air gap will increase, then definitely your torque and speed torque will drastically change. If you go think about the more power density motor. So dimension are more important, more critical things when you are designing the motor. It is not a job of only the mechanical or any other engineers. It is the electrical designer or mechanical designer. Both should jointly work and solve the issues, and make some tight tolerances to achieve the good output. So these are the tests which is required. I already told you these are the basic tests. Type test we can call it as we have to measure inductance, resistance, everything. When these are the primary inspection of motor, means before installing before put over the dyno for the performance testing, we have to go through such kind of test. So where we can get a best performance, or we have to validate our motor. Otherwise, suppose I'll give you one example. If our motor is loaded over dynamo, before that the winding resistance is imbalanced. If the winding resistance is imbalanced, then your current would be imbalanced. If your current would be imbalanced, then definitely your torque would be you are getting imbalanced torque. Some ripple or something is happening there, or it will cause of vibration, or we can say the damage, or which will reduce the life of your motor. So every test, every passive and active test have their own importance. So after designing the motor, after prototyping, you should go for some kind of test. That's the type test you have to perform. Then load your motor for the performance. These are the standard which is available. That is a NEMA, IC, ISO. Then these are the standard which will help you for while designing the motor. They will also define some boundaries. They are in some standard. You are getting some ready-made, or you can say some standard housing. According to that, you can design your motor. You can take dimension reference outer OD of your motor from there only. So these are the we can say the important part of our motor designing. You should consider standard, and you should qualify the standard. Suppose some standard told you your motor should be work for X time. Maybe I'll tell you the AI041 currently. ARI is following the standard. They told you your motor should withstand, your motor should work for 30 minutes continuously at your rated top speed. The variation is not more than plus minus 5 to 10%. So these are the design inputs which is coming from the standard as well. This is one input source for your designing as well. Okay, thank you. So any question? If we are not covered in this topic, then please text me. I'll answer you through mail.
Oh, because thank you for the presentation. That was amazing. Yeah, so informative from your end. Jason, is there a question?
So because there's a question that's in the chat which is raised. So the question is talking about which motor to use for regenerative power and to charge the battery, and which technical aspect should be used for this. Basically, the question is more on regenerative power. Yeah.
Yeah. So basically, what happened? I'll go. So when we are thinking about the motor, so basically when we are thinking about the regeneration, so BLDC or any magnet motor, not only the BLDC PMSM, any motor where we can use the magnet, which is helpful for the regeneration, because induction motor, PMSM, SPMS, any magnetic motor work as a generator while we are providing some forces, or we can say where we are rotating their rotor in the magnetic around the magnetic wire. So currently you can say here this is the IPM motor. If I rotate the rotor, then it will create it will induce the magnetic field. It will generate the electricity. But for the reason, I'll say reason, when we are going for the reason, we have to consider our MOSFET, we can say the current limit, even though we have to think about our battery SOC. Reason is possible with any kind of magnet motor, but we have to think about our battery limit. Suppose if you are at any slope, and your motor is operating at very high RPM, maybe 8,000, 10,000, beyond your rated speed. Suppose your rated speed is 4,000 and you are in a slope, then you are going very fast, your velocity is very high, so your back EMF which is generating is very high. It is suppose 110 at 4,000 RPM, it is a 48 volt. But at 10,000 RPM, if it will hit up to 110 or 120 around that, then definitely it will damage your MOSFET. Suppose your MOSFET is capable to withstand such kind of, we can say, the back EMF, then it will hit your battery, because your battery having some limitation. When you use very high voltage around the battery, it will damage your battery as well. So for reason, not only the motor type is important, also important to consider your inverter switches capacity, your battery capacity, current capacity. So most of the time, such type of condition is arise. So people is used to going for the active short circuit kind of scenario, where we can, if our back EMF is hitting beyond the critical limit, people is short the winding turns, or you can say the phases, and apply some brake movement over the motor. Yeah, that's all.
Thank you, Vikas, for that answer. So another question which is related to this is some questions have some students have a worry on that they are from electronics and communication engineering, and they want to design motors and stators, and for any further doubts and clarifications after the webinar. So from Bosch IEEE side, we'll be sending a document on the scope of each of the problem statements, and also some literature survey, and because we will also be able to share your slides with them, correct?
Correct. Yeah, we can share this presentation. If some student having query, so please text. You just share their mail ID. So and after that we can take all the their doubts and we'll reply. No issue. Over the mail we can reply.
Okay, perfect. So we will also be sharing a Google form as mentioned earlier. So you can post your queries there, and we can get them clarified by Mr. Vikas. Okay.
Yeah.
Okay. All right. So yeah, Vikas, please.
Okay. No, please.
Yeah. Last question was, why is it that when we start an electric motor, we hear a humming sound at low speeds? That's the question.
Yeah, basically what happens, the cause of humming is, various causes are there, but I'll explain you the single one. So basically what happens, when we are going for the when we are thinking about the frequency of your stamping or any your material will be, if suppose this frequency will get in a resonance. Every material having their own frequency. own physical, we can say the fundamental frequency, where when you hit them, they can oscillate or try to oscillating with their natural frequency. When we are going for the electrical frequency, because of the electrical frequency, because of frequency we are getting some attraction repulsion kind of force, and because of that force, some we can say there will be some mechanical frequency will be created. The frequency of that component, the frequency which is generating from our electrical frequency or electrical operation, if they both are the matches, then it will create a resonance, and because of resonance the sound will come out from your any can say the object, not only from the motor only. Even though if you have two dissimilar metal, or you have two component with you, metal component with you, if you matches their frequency, if any component which is the which is similar to that natural frequency of that secondary component, if you vibrate, or if you can say the hit both the component, so they will create a resonance, and because of resonance, noise and vibration will be generated more and more. So that is one of the best we can say reason behind this, why humming is great. Mostly in transform you can observe such kind of vibration. And even though if your stacking, when during mass process, your stacking is not correct, or if your stacking is not proper, at that time your resonance will again goes high, because they don't have to restrict or to mitigate or to absorb such kind of vibration, you can say the forces. Yeah.
Okay. Thank you, Vikas, for that wonderful detailed answer on that question. Okay. In the interest of time, there are actually three questions. But some of the questions we will also be addressing in the next session. For example, why is inverter used in electric vehicle? We have a session on design and control of inverter, so we'll have that question answered there. But one answer that one question we can take forward now as a last question is, how should we select these motors and on what basis? Maybe we can end with this question.
Yeah. So there are various factors are there, but I'll tell you the one only, because we have limited time. So basically what happened, if you go for the lower capacity motor, maybe 10 watt, 20 watt, 250 watt, 1 kilowatt, 2 kilowatt. So if I go to use the same motor for the traction applications, you can suppose I have option of induction motor, I have option of BLDC motor. Now I'm considering two only because of time. Suppose if I go for the lower capacity motor, if I want to build 250 watt motor for the cycle, if I use induction motor, so I'm getting less efficiency, because most of the losses are the we can say the limitation. Mostly the losses in induction motor are in less can say the lower power motor is high. In case of BLDC, the losses for the same motor and a lower capacity, it would be less. So because of that, we are going for the PMSM. If PMSM or BLDC kind of motor, and even though suppose we are taking the same motor for the higher capacity, where we can say we cross the threshold limit of the efficiency, because most of the losses point are reaching their boundary limits. So in that case, even though with induction motor we are getting I4 efficiency at a higher kilowatt rating, because they already escape their losses boundaries. So that is main, we can say the first one of the, we can say the difference why we are going for the PMS and BLDC for the less rating. And even though controlling is also easy, that is another part. So now I am not discussing, but I'll text you through the mail in detail.
Okay. Thank you, Vikas, for that wonderful explanation on this session. I'll hand over to Praveen to introduce our next speaker. Yeah, Praveen, please.
Yeah. Okay. Thanks everyone. Thanks for your cooperation, and it was nice audience, and thanks for the opportunity. Okay, thanks. Bye.
Thank you, Vikas.
Thank you, Vikas. So for our next speaker, we have Uh, So for our next speaker, we have Dr. Jivanand. So currently he's an assistant professor with the electrical engineering department at IIT Roorkee. He did his PhD from IIT Delhi. His research interests include topics related to e-machines, power electronic drives, and renewable energy systems. So I would like to welcome Dr. Jivanand. Dr. Jivanand, are you on the call?
Dr. Jivanand, you are self-muted right now. Yeah, can you try to unmute? Yeah.
Yeah, is it audible now?
Yes. Yeah.
Yeah. So I was trying to unmute, but it was showing you have been again muted. So I don't know what happened. So it doesn't matter. So let us start. I think, is it visible? My screen is visible?
Yes, it's visible. Yeah.
Okay. Thank you so much. So first of all, I thank the Bosch team for this opportunity to interact, and it has. I thank you so much, and also the associated people who have made this possible, like Sadeep and all this, and Prashant and everyone, and all those people here, like Amaya. I don't know all of them, but I thank all of you for this opportunity. I start my session. Before starting the session, I just want to just a brief introduction, because most of the people here might not have come to this Uttarakhand or Northern Institutes. Delhi, definitely most of the people might have visited, but just a brief about the institute is like it started in 1847. It started as Thomson College, the first engineering institution in the British Empire. So it's the oldest technical institute in Asia. So then 1949 it became the University of Roorkee, and IIT Roorkee in 2001. So this is the brief history of this institute. You can see this is the main building. It's a very big sprawling campus. So all of you are invited anytime when you come in official or otherwise. So this is the topic today is trends in AI applied to diagnosis of drives. So actually this is a very generic topic. It is not very specific in the sense drives is an integral part of EV. I think the last presentation was on machines. I didn't listen it fully. But anyway, so all this, drives is an integral part of EV, and you can say it is the most important part. You can arguably say so. Drives is one of the most important part of EV, and onboard diagnosis systems is gaining importance in EV systems, because you need to diagnose the fault, at any electrical components such as motors or power electronic components, etc. at the earliest stage. And then take corrective action, or you should be able to say at least like it would also be good if you can say that how much time that EV can survive, or that particular component can survive. That would be a very good indicator or knowledge which can help to schedule the maintenance or take some corrective action. So it is also important in applications such as marine and aerospace, because there you don't have much time. So if you know that the fault, some issue is there, some fault has occurred, and then you also know how much time is remaining, then it becomes very critical information to land the plane in the nearest airport, or maybe the nearest port, for example, for the marine. So, and also today's time, we all know that the more electric aircrafts and more electric ships are being coming up. So because all these mechanical things have been replaced by electrical counterparts. So this more electric has a is the trend today. So it is important in that aspect also that this drives diagnosis or electrical component diagnosis or power apparatus diagnosis is very important. if you take in that aspect also, all the aspects, if you see, this problem is very critical for any kind of industry. For example, process industry or aerospace or marine or any of these things. So that is the first thing which I wish to share with you. So now going to the presentation. So we have it because this there is an introduction, there is maintenance strategies, different techniques, and then since this has a kind of flavor of AI, so I had put some of our works on deep learning architectures which we have developed and published, and some ongoing works and other works, projects and publications which we have. So this is the brief outline about this one. So let us go one by one. Importance. So what is the importance of this project or this kind of a work? So we can see that anything which we try to explain, we take one example basically. You know? So so I have taken an example of an induction machine, which is a very traditional motor. But even if you see, it is used in EV even today. So there is a modified form of the induction machine which is used in many of the EVs, some of the EVs. There is PM machines, reluctance are also used. But diagnosis is a generic thing. So you need to do diagnosis for any of these electrical components or drives. So I have taken a small example of an induction machine to show you that different type of bearings, shaft, rotor, stator, all these things are there. So if there is a fault in the stator, you can see that how much the machine can damage the right side. So it's a irreversible damage, right? So we need to stop this so that the downtimes and the economic loss will be minimized. So before long, if you see the maintenance strategies, if you see, because we need to know a little bit of history, because maintenance strategy started with breakdown maintenance. So something gets wrong, people used to fix it. So if you see in the 1930s, 1900s or 1940s, this is what the breakdown maintenance means. So afterwards, in the last 50 years, you can see 50 years or so, or more than that, the time-based maintenance, scheduled maintenance started. So every 6 months, no matter what, you open every components and electrical or mechanical, everything, and fix it, or maybe oil it, or maybe check everything is fine or not, whether you want it or not. So that is called time-based maintenance. Now that strategy is also not efficient, because you waste your time and effort even if you do not get sufficient results. I mean, whether you want it or not, basically. So now the trend is condition-based maintenance. So in this case, what we do is we find out online. So that's what I said in the beginning. It's onboard condition monitoring. So in EV or is all online condition monitoring in other applications. So you have the electrical component, and then you monitor the condition every instant of time, or maybe in certain instance of time, and then take corrective action based on it. If there is a problem, then you take action. So it's online basically. So that's the kind of strategy which is presently sought after. So because this presentation is more about the industries involved, so industries doesn't invest unless they find a reason for it, right? So why this problem is important for industries, because you can see so this is an interlaminaire stator fault, which is 430 megawatt generator. Now, so if this fault occurred, the reason, let us not worry about that. The estimated repair cost was $17.5 million. You can see the repair cost was this much, and the loss of revenue for the utility because of this, what shall I say, the downtime was $270 million. So what happens is, this kind of a, what shall I say, huge economic loss is will occur if you don't properly, take corrective actions at the right time, or you don't investigate at the beginning itself. So this is one example which I have taken from this is a patent, so this is a paper. So this is the kind of thing which we are looking at. So basically what we need for the diagnosis systems, basically I told you this is a very generic topic, but yeah, if you take a particular example, it will be easier for understanding basically. So if you take, for example, if it is a machine, you have different signals coming from it. For example, you have motor, currents, voltages, vibration, acoustics. So all these measurements you take and extract the features, and based on that you take a fault decision. So what you can extract from that? So you have the different signals with you, extract certain information, and then you take a decision on that. So you have a lookup tables, knowledge-based systems, etc. On the other hand, you have experiments and FE models, etc. So all these things will give you information, and you extract it and then compare with the baseline model to take a fault decision. And then comes the post-fault operation. So this is a very generic overview of the fault diagnosis system. So the signal can be, I told you, motor current, voltage, vibration, acoustics, etc. So this is a very, very generic overview of the fault diagnosis system. So I just wanted to explain with the example of an induction machine, so that it will be clear. So you see, before we go into the AI-based techniques and other things, basically what is how the fault manifests is important. This we need to understand this. Otherwise, we cannot appreciate because artificial intelligence techniques are actually supported or needs in inference. They are inference-based techniques. The inference comes from the model-based techniques. So this is a mathematical description of an interturn fault. For example, you can do any type of faults like broken bar or bearing or any kind of fault, or maybe the laminar faults, anything. So, but this is a particular fault called interturn fault, and it is NAS2 is the number of turns involved in that fault, and RF is the insulation resistor. So, see, this is the kind of mu. You can see that it is the percentage turns involved in that. So, so you can see that this is the kind of physics of failure model. So left side you can see this healthy stator. This stator is common. You can see, in permanent magnet or reluctance motor, any motor you take, the stator is the same. Three-phase stator, it doesn't mess. Unless, even for multi-phase machines or polyphase machines also, things are the same. So you can see that this modeling also will be the same, right? So now I have generalized it. Anyway, but let us take the case for the induction motor for our simplicity. So this is the two variables. You can see the insulation resistance and also the fault level here. So these are the two variables to define the fault. So now let us not worry about the mathematics. Let's go here. So you can see that this particular two figures we have shown here. In the left side you can see, I think all of you, I hope the students I am addressing to the students actually who may be listening. So you have seen in the laboratory, you may have done experiments in induction machines, synchronous and all these things. So you already know the equivalent circuit of an induction motor, etc. Right? So in the left side, you can see there is a positive sequence fault circuit, negative sequence fault circuit. So I hope you must be also aware when does this negative sequence comes into picture and all those things, right? So just you can give a food for thought. I have decomposed this faulty model, this particular faulty model on the right side to two different circuits in the left side and the right side. So it defines that particular condition. So whenever there is an abnormality, there will be a negative rotating component, and then the double harmonics comes, and all these things are there. But what is this two circuits I have shown? So can you just see and think, which circuit will be better and which circuit will be good for analyzing the fault? So you can see that the fault manifests, or in the healthy case, there is no mu, there is no IF, etc. Right? You can see the positive sequence fault circuit. You can see that the fault will manifest as a current source here. You can see 1/3 mu into IF. In the negative sequence circuit also it manifests as 1/3 mu IF. Let us forget about the derivation and all this mathematics. But you can see that additional term is added to the healthy circuit, right? So of course negative sequence can also come in whenever there is a voltage imbalance also, right? When a voltage imbalance comes, definitely if you are in power system, definitely the voltage unbalance factor will be there, right? So that also can give you a negative sequence. And also the fault can also give you a negative sequence voltage and the circuit. So you can immediately tell that, yes, whenever there is a fault, there can be a negative sequence for this one voltage and a current, right? Or you already know from the basics of this power system that whenever you have a symmetrical component analysis and all those things, whenever you have a imbalance in voltage, also you have a negative sequence. So but let us. I am not talking anything about this voltage imbalance, but you can correlate. No? So, but if you see these two circuits, can you just imagine which one will be better for analyzing the fault? There are some typical characteristics for these circuits, right? So maybe I can tell you that if you see the right hand side circuit, you can see that there is a term which is dependent on the slip, basically, right? RR by S is on the left side, on the right side it is RR by 2 minus S. I'm not explaining all these inductances and all, you are already aware of it. So, 2 minus S, so you can immediately say that slip varies for an induction machine, maybe class A, B, C, D. You see, class A, B, C, D, the maximum it can go up to 9%, worst case. So this will be S will be 0.09, worst case scenario. So, see, but still, you see, it doesn't make much of an impact on the right hand side circuit, right? I hope you are getting the point. So, but it does make a big significant impact because it is RR upon S. So the right hand side circuit is nearly slip independent or load independent, right? So now the research starts here. So there were some 10-15 publications which came out after this, just based on this circuit. So you see, that is the way people think. So this is not dependent much on slip. Let's try to investigate it and find out some indicators and blah blah all this. So many papers came. Of course, it was reciprocate, because if I tell this, it is equivalent to telling about all the machines, because the same thing was worked out in PM machines and all these things also. So people think in similar ways. So because the reasons are the similar. Right? So and also you can see the ISN is a current drawn here. No, this is the negative sequence current. It is split between the two. There is a mu by 3 into IF, which is the fault component, and ISN1. This ISN1 is basically due to if there is a voltage imbalance, this current will contribute to that. Right? Mu by 3 IF is due to the fault. And the remaining part of the circuit, maybe some imbalance is there, like this voltage imbalance and all these things. So it is a sum of the two. So all these things needs to be catered by this particular current only, the ISN. So just by observing the current ISN, you cannot say whether there is a fault or not, because it gets confused. Because of what reason it is there, whether it is a good fault, whether it is the voltage imbalance. So again, people started thinking, then they worked out in impedance-based techniques and all these things. So because our talk is not focused on the model-based techniques, just I will not go into those things, but it will definitely help you to understand the importance of the model-based techniques and think further in this direction. So I am not going to the impedance-based methods which developed after that, but just briefly I wish to tell you that out of the different signatures which we discussed some time back, the motor current signature analysis is the most sought after, right? So it is a non-invasive method, because you don't need to, suppose you take a vibration sensor, you have to put it on the machine, disturb the machine. But in the case of a current sensor, you don't need to disturb the machine. So it is already a part of the drive scheme. So that's the advantage here. So I don't know, many things are written here, doesn't matter. So basically there are some specific stator fault frequencies which appears when there is a fault. So there are some methods, people developed, some methods which works for the line fed machines may not work for the drive fed machines, right? And see the permanent magnet machines, they used to monitor the second harmonic component of the Q axis current. So you have the vector control drive. So that harmonics will help you to detect the fault. And so that and also and one more problem is that if you transform to the frequency domain, you lose certain important information. So we need to be very careful when we directly transform it to the frequency domain. For example, if you see this particular graph, why I put this graph? Because this is a the different frequencies which will come up when there is an interturn fault or a stator fault. The 75, 125, 175 hertz will come up. You have seen this equation. I'm not explaining those mathematics, but these three frequencies will come up. If you see 75 hertz is here, this is a constant slip condition, the left side graph. 125 hertz, you can see there is a peak here, and 175 hertz also there is a peak. But if you see the varying load and non-constant slip, you can see that everything is very smooth and You cannot make out what is happening where. Of course, there is a 150 hertz or something like this, but you cannot see any other frequencies. So then it becomes difficult. So directly converting into a frequency domain doesn't give you anything. This is the problem. So it confuses you rather than convincing you, right? So then we go to other analysis techniques like the envelope analysis, right? So you have envelope analysis is interesting because you have, for example, if you take a broken rotor bar fault, we have seen a stated fault. The broken rotor bar fault. So you can see this is the drive scheme here. So 4 broken bars. So the envelope will contain 2 into slip frequency, the envelope of the 3-phase envelope. So there is a profile modification for interturn fault for the envelope, for the 3-phase current envelope. So if you isolate this envelope and then train some classifier or something like this, like a Bayesian classifier, a maximal likelihood classifier, then you can diagnose the fault. So, this kind of techniques people started to look at. Another interesting technique is wavelet based analysis, which can also be used for voltage source inverter fed drives and induction machines and all these things. And there is also other techniques based on EMDs, empirical mode decomposition. You decompose the signal in different oscillatory modes into the intrinsic mode functions, which are nearly speed independent. So these kind of techniques also started to coming up. Maybe you can say these things came up around 2000. I would say that it is, I'll tell you, 2010, around that time, right? So you can see whatever we discussed now, I have put it briefly in this slide. You can see that the different, I have not discussed everything because I have deleted a lot of slides because our topic is little bit on artificial intelligence. So the negative sequence current, deviation of diagonal sequence curve, negative sequence impedance, voltage mismatch, all these things, these are basically based on the voltage and directly from the voltage and calculants you calculate. So they are non-invasive and fault sensitivity is very high for the second technique. So I told the negative sequence current, the fault sensitivity and fault isolation is low. I think you can directly connect to that circuit because why it is low? Because it gets confused with the voltage imbalances. The negative sequence voltage current develops also due to the voltage imbalances also. So that's why the fault isolation is low. So there are people developed with other techniques to do that to make it better and all these things. And signature based negate, some other flux based current, electromagnetic or vibration and all these things. So some non-invasive methods. So this flux based, you need to install the flux sensor. So it's not a non-invasive method. Current, yes, it is non-invasive. Electromagnetic or you need a torque sensor, very costly. Vibration, you have to put the sensor. It is not non-invasive. So this fault, again, you can see the fault isolation, the maximum is for current-based techniques. This is based on the broader umbrella. This is specific to the current-based in the top table. So you can see these kind of things start coming up, which gives you more idea, information about how to proceed and why and what these questions can be answered. Now, again, going to the next, this one, AI-based methods. The AI-based methods, you can see that initially they started developing these model-based methods and all these things. People started to understand that things are not so looking good. So they started to go to people started to start applying this positive sequence voltage, negative sequence voltage, positive sequence current to neural networks, and then estimate the negative sequence current and the actual current. They take the difference and then find out the fault. Right. So this is a moving basis neural network. So unsupervised models were also developed, and NFIS-based models were also developed like this. Supervised and unsupervised based methods started coming up. Basically, you can see that the NFIS, the fuzzy neural network-based models are also coming up because it can also takes into account the machine construction asymmetries, and GES can be used to train them. So this is basically the trends which were there up to 2013 or so, right? So, but after that, so basically you can see that the traditional techniques as the model-based technique, which I told about briefly in the beginning, so it has moved to the AI techniques. Signature extraction, fault identification, fault severity values, everything can be done. So AI techniques, as I told, is a broader umbrella. It can be applied to fault diagnosis, system control, and stability analysis. So all these complex relationships can be modeled and accommodated using an artificial neural network. So this is the brief summary about the trends. And you can also see, if you see the techniques, The current signature analysis, as I told you, it is a non-invasive kind of technique. So the severity is, you can see that the MCSA can detect very low severe faults, that is less than 1%. You can see that. The current envelope technique we discussed, it can detect up to 0.42. All other techniques are also there. Here I'm just highlighted the red one because they can detect very low amount of fault also. So the impedance based EPMSM, it can detect 0.23% fault. Synchronous measure total field voltage, it can detect 0.32% fault. High frequency injection method, they inject high frequency into the control loop of the machine and then to observe the response. So that can detect up to 0.3%. Neural literacy or the continuous online training network, so that we discussed recently, so that can detect up to 0.51%. And you can see that generally the neural net unsupervised learning is a big failure actually. It can detect up to 20%, which is not a very good rate. So this is about, briefly about all these different techniques and all those things. But what we can understand is that analytical modeling is the fastest method. So when you have a mathematical model, instantaneous current and voltage, this is the best thing to do. Analytical modeling is the best. But what happens is the accuracy of fault diagnosis, diagnosing the fault will be lesser. So the finite element models, again, I have not discussed those models in this. It is most accurate, but time taken is very high in that. So we don't generally prefer it for online or onboard diagnosis. But artificial models, one strength provide a fast and accurate simulation of the machine, but need training. So they need training and testing in the other. So people have done everything already. So what is the inference? So it's all depends on you. So if you are okay with the fault, say level of 3%, then you can go for a model-based method. So that's a decision which you have to take, right? So, but anyway, this is about a brief thing. So I think going to the next stage is I wish to put some of my works, our works actually, in the AI based because this talk has some flavor of AI. So we have done some works on drives diagnosis, which is so the deep learning is the next stage. Basically, we have talked about AI and all these things. The deep learning means actually it is it is artificial intelligence based method like machine learning only, but it can handle a huge big data basically. For example, as SVM classifier, if you take, it cannot handle a very huge amount of data like CNN or other kind of deep learning techniques can handle. And essentially, it is the same thing, but it has a better architecture, a very huge architecture which can handle those kind of applications and data, which cannot be done by traditional AI based methods, right? So nowadays the AI has gone much far. I mean, it has now gone to, I think the ChatGPT and all these things have come up, and you can see that it has gone to generative AI. Generative AI means it can find out, it can actually, conclude or take it. So, I mean, generate certain, decisions of its own through learning. That kind of so they use transformers for that. So it has gone to that level. And also I can tell you one more thing which is interesting in AI, because if you give different, I don't know how many of you use the ChatGPT and all, different inputs will give you different results. For example, if I say that I am Jivan and I am from Roorkee, can you tell about coffee? So it will give one result, because it will connect that result to my name, maybe. Okay, my name is a little bit Kerala or Tamilian, so it will add some coffee. It will say it's brew coffee or something. It will add that also, that information also with the result. Suppose you say I am maybe Samuel, I am from USA. Can you tell me about coffee? Then it may add something else. So in fact, it should not happen. But there are some glitches also in ChatGPT kind of applications which I have noticed. So maybe a computer science expert can also tell you more about it. But our application for the current scenario is about deep learning architectures for IT fault diagnosis. Before going into these things, let us go to the more fundamental things. Let us CNN and LSTM are the most widely we have used in our research for diagnosis applications. CNN is more convolutional neural network. I think you must be aware of what is convolution operation in signals, basically. If you don't know, you can go through any n number of materials are available. But in the case of CNN, that reversal operation is not there. of convolution. So that is the difference here. So if you go to the CNN, so this convolution operation here, for example, if you take a matrix and just explain the convolution operation. So this is a matrix. You can see this is 6x6 image. Let us take it as a matrix. Doesn't matter. There are two filters here, filter 1 and filter 2. These coefficients are found out using algorithms like gradient descent or so on and so forth. But if you see, these are the network parameters to be learned. That's what I have written here. So they need to learn these network parameters. Learning is through algorithms, right? Each filter detects a small pattern, 3x. So you can see this 3x3 pattern. You can see this is the filter 1, right? Let us forget the mathematics. Let's not worry about that. So this will put this filter on this image, and then what happens is you scroll it. This is a dot product. You know what is dot product, I hope. And then it gives you the dot product is 3 here. So you get stride is 1. Stride means it is actually, I'll show you, it will show by itself what is a stride. This is stride 1, right? So another dot product. This is stride is 2, then it becomes, is doubled basically, right? So this is how it is. So now let us take the case of stride 1. So you can see that, it comes to be like this. So, the whole thing has come. So it has come to how many it is? 4 cross-core matrix, right? So 6x6 to 4 cross-core. Now it is another filter. This is a filter 2 actually. Repeat this for each filter. So this is repeating here. You see? Now it is, it is going down and all these things. So feature map. This is the feature map as we made now. So that is a 2 or 4 cross-4 images from forming 2 into 4 cross-4 matrix here. Interesting. So now you can see this is actually filter 2. Filter 1 results are here. Filter 2 results are here. Now we apply something called max pooling. So that's what is shown here. FM equals max FMN. So you can see in the left side, there are 4 red square boxes. You can see. So what happens? It is max pooling of size 2 means it's a 2x2 matrix. You can increase also. Doesn't matter. So you can take the maximum of simple it is. The maximum of this 4 is 3, right? So it will give you 3 here. Minus 3, minus 1, 0, minus 3, it is 0. So something like this, it does for everything, right? So we have got some numbers here now. Then let's see what happens after that. So this is now taken out like this, and then it is flattened. It is flattened like this, and then it is given to a fully connected fluid column neural network, which is basically based on weights, biases, and learning. So this is how it works in the case of CNN. Similarly, you can see, these things you can see also in the case of an LSTM. This is the input convolution max pooling. Again, see, this is a continuous process. So this is flattened and given. So basically, after that, instead of flattening and giving, you can also give it another convolution layer, another max pooling layer, etc., etc. Right? So this kind of a structure we can observe in the case of a convolutional network. Similarly, you can see, so this is the mathematics again, m minus f plus 1 cross m minus f. M is actually the size of the input vector, f is the filter size and all these things. So what do you get out of the first layer, first convolution layer, and then pooling layer. So max pooling layer gives you dimension output of k by p. So let's not worry about it. You will see that when time comes. So another important point, I just want to tell you this, this part I have taken it from some website. So this is actually LSTM. LSTM is also basically a kind of a network which is an extension of, you can say that it is extension of recurrent neural networks. Recurrent neural networks are used when you need to remember something. Recurrent neural networks, you need to remember something, right? So then it is very good for predictive purposes. This is a forget gate, input gate, and output gate. Right? So you have a short memory here. So you can see that there is a short. So it's one of the unit of the LSTM. So you have a long-term memory and short-term memory. So long-term memory means some things are like it's a kind of a thing which you need to retain for a longer time. Short-term memory means sudden changes comes. So that's called a short-term memory. So you have a say take one of the cells of this LSTM. So you have a short-term memory, you have a weight and a bias, and so you create a potential memory to remember, and you use there are different type of functions here, like sigmoid and tan sigmoid function. Fundamentally, what it does is the transit function you can see here for a potential long-term memory. So that actually creates a new memory, and percentage how much of that new memory you need to remember is done by the sigmoid function, right? So you add it to the already existing long-term memory, then to produce a new long-term memory. Similarly, from this new long-term memory, you create another potential short-term memory. Again, using a transit function, and they use a sigmoid function to scale or to find out how much of that short-term memory you need to remember. The output of this unit is basically a new short-term memory. The input is the input which you give at this point. So the first gate is a forget gate, input gate, and output gate. So these three gates are used. So this particular picture I have taken it from. I think I didn't put the source here. I'm sorry for that. So this has actually the advantage that the recurrent neural network is shown on the right side, but the recurrent neural network has the problem of vanishing and exploding gradients. So this is a really unit. Let's not worry about that. So it will avoid that problem, right? So let's see how it is working in action. So we came from here. Let's go. We came back to the same place. So we have just a brief idea about CNN and LSTM now. Now it is time for us to understand like how it works, right? So for example, in our problem we have a data of currents basically. We take current data and I have converted that current data into 2D using recurrence plots, right? And then using, so 1D to 2D conversion I have done here. And you can see that 64 per 64 matrix. So taking inspiration from what we learned just now, we can see that, this is 63 cross 63 cross 60. So basically m minus n plus 1. So you can see I am taking a 2 cross 2, this one here. Right, so 2 cross 2 means what is m? M is 64. 64, it is m minus n. 64 minus 2 plus 1. So 64 minus 2 is 62 plus 1 is 63. Right? So this is 63 cross 63 cross 16. What is this 16? 16 is a number of filters. So I have 2 cross 16 number of 2 cross 2 filters. That's the kind of mathematics here. So these filter coefficients are identified. That needs to be learned. That's a different matter. Okay. So now, and then you go to the max pooling layer. You see here it is 31 cross 31 cross 16. This is half of that approximately. And then again, you give this to another convolution layer. So another convolution layer, there are 32 filters here. Let's count 32. 32 filters. You can see that m minus n plus 1, 31 minus 2 plus 1 is 30. So this is actually into 32 will come here. 32 such filters are there. Again, it will go to the max pooling, which will give you 15 cross 15 cross 32. And then again, it goes to the another convolution layer, which has 64 2 cross 2 filters. So this is a repeated operation. Like this, it goes to like this it goes. See? It's interesting. So last layer is 3 cross 3 cross 64. I decide, okay, but now it is fine. So how you decide? That's the question here. How you decide the number of layers? It is a hyperparameter optimization problem. You can do it in trial and error method, or you can also do it using, some sort of optimization also. But we are not interested in optimizing these things. We are more interested in applying it. So we did this in trial and error. Okay. So now let's go to the next level. That is the first level. So we have an SVM here. So why do you want an SVM? SVM is also another kind of machine learning which people might have used it before. It belongs to a little traditional machine learning algorithm, but a very successful algorithm for medium-sized data. Right? So we have 2 layers of SVM here. This is a multi-class classification. So first it determines whether there is a healthy or a faulty, and if there is a fault, then it goes second level and the degree of fault, severity of the fault also it determines. So this is the kind of an architecture which we have. So this is a combined architecture, that is hybrid architecture. It combines the good of convolutional neural network. The convolutional neural network is a good or a great extractor of features. Features it extracts very nicely, right? And now, I mean, the SVM is a good classifier. So basically, we have used the good of both words. Basically. So HCN is a very well-established machine learning, deep learning algorithm. This is a hierarchical structure, and SVM is a very good established algorithm in the traditional machine learning domain. So that's how we can combine it. And you can also combine, like this, you can combine flat diagnosis. So you have another structure, which is a flat. So you don't go to the two level, like hierarchical. You can also put it, you can also put an LSTM of it. So instead of a, what shall I say, fully connected layer and SVM, you can put an LSTM with dense softmax layer. So directly you can classify without going to a hierarchical structure. Okay, so that's another way of doing it. You can also do it using one-dimensional data also instead of going to two-dimensional data. You can here we converted it to two-dimensional. You can also do it using one-dimensional. That's no problem. Similar operations happen, right? So because of lack of time, I am not explaining everything. So some results we have obtained. These are all published works in our. We have published these works in. I think this paper came in IEEE Transaction Industrial Informatics. So anyway, so this is the accuracy. You can see that performance of the SVM, HCNN combined, which we just now discussed, is you can see that there is a very highly accurate results we are obtaining for A, B, and C currents. And testing time also, you can see it is very less. When we should deploy, this is the time it takes to give results. So typical HCN, so typical hierarchical CNN softmax. So without using any hybrid methods, you can see that the accuracy is good enough, but not as good as HCN and SVM. But the testing time is also slightly higher. But if you can see the below one, the last one is interesting. This is performance metrics of SVM. This is you can see that the SVM, the training time. You can see the training time is all similar for the first and second. It is 400 to 500, etc. But the training time for the third one is 2200 seconds, and the testing time is 4 to 5 seconds. So what happens is that this is a clutch here. So the SVM, even though it is an established, well-established actually algorithm in machine learning, it cannot handle big data. This is what it shows. So training time is much more required for the case of SVM, but the testing time is kind of you can see that is also higher compared to that of HCN and SVM and HCN and softmax. So that's why that's where this clearly shows the advantage of using deep learning techniques in drives basically. And also you can see that this is okay, and 1D and 2D has a better feature extracting capability. So you can also see more closer results. That is, you can see that this is confusion matrices for phase A, all the three phases basically. You can see that the confusion matrix for hybrid HCN and SVMs, you can see that this is the diagonal. You can see it's very high accuracies you can obtain. And the second row, you can see that the typical HCN, and you can see that this is, for all the three phases, it is good but lesser than the first row. And the third is for SVM. It is an optimized SVM basically. So you can see that is much lesser compared to the first and the second, which we showed. So similarly, you can see that the flat diagnosis structure, which we discussed, without going to the hierarchical, it has computations are less, and also the memory required is also less, and time required is also less. You can see that. So I am not going to discuss all these things because of the lack of time. We can see that we have also done GRU and all these things for the diagnosis purpose. Maybe you can read these papers. Then, if you have any doubts, you can get back to me also. All right. So I think one more we also do work on permanent magnetic fault diagnosis. So this is a residual based techniques which is published work. So basically, you have you observe something in the positive sequence frame and convert it to negative sequence frame and then extract it as a DC component. So that this is some other work, some related works I am showing, so which we do in our laboratory. So this is for the PM machines basically. We also work on synchronous reluctance motors. This is a trend today's time for what shall I say, for EVs and so on and so forth. So it needs to have a high saliency ratio for giving a good power factor. So we also work on these kind of projects. It's ongoing work on diagnosis techniques for SynRM and all this. So that's about condition monitors. I think I had a short discussion before the talk with Mr. Sadi. So he was interested in this grid connected transformer PV inverter. So I think I thought I'll put this out. We are also working on this topic. So a couple of more topics we work, but I thought I'll put a short about this so that it will be adding some value to this talk. So I think this one, what we do here, basically I'm not going to detail because it will take more time. So maybe another talk I can do this. But briefly, this it's a totally different topic. It's not at all related to the previous one, but it is a very important topic because today's time we use the PV panels and all these things. So DC-DC converters are much prevalent. But you see, this PV panel output is DC, low voltage DC. So we need to boost it and connect it to the grid. And multi-level inverters also come into picture. So basically, the problem here is, you can see that the problem here comes when you have a leakage current issue. So leakage current, so you can see this is a PV panel components, the left side down, you can see aluminum frame, between that you have the insulator. So you have a capacitance there. So this kind of leakage capacitances are also there. Here you can see this is a panel to the ground. You can see that there is a leakage capacitance to the cell to the panel rack. So mainly to the panel to the ground contributes the maximum, right? So you have a German standards where you have disconnect the PV panel. If you have a leakage current more than 30 milliampere, sorry, disconnecting time is also given here. So you cannot afford. So these leakage currents are high frequency currents, maybe, and so they will interfere with the communication lines and all those things, and they will cause EMIs, right? So that's the problem here. So this parasitic capacitance is an issue. Let's not. So again, some other terms such as common mode voltages and all these things will come. But what I'm not going into the details. But what we do here is, I'm skipping all these things. So the common grounding. So what we have in our research group we are doing is a common grounding based method. So we have also published 3-4 papers in the IEEE this topic also. So what we do here, we directly connect this. So the common this leakage current part is can show here. So this ground, we directly short it. So the common grounding we do. So you can see that this ground is directly connected. So this capacitance is bypassed basically, and this capacitance is shorted basically. So this common grounding will eliminate the leakage current basically at the source itself. So this kind of common, there are other topologies like AC decoupling, DC decoupling, midpoint coupling, and so many things are there. So, but this is a recent trend, and based on this common grounding topology, there is a switched capacitor based circuits we have developed, and these have been hardware demonstrated. And this one particular circuit is I am just showing. So triple boost. 3-level triple boost common ground switched capacitor, grid connected transformerless PV inverter. So basically this is actually a different topic, but anyway, it doesn't matter. Just I am showing you for this one. So you have a PV here. So you have a 3-level. It's a very basic one, but it's a new topology which was published also. So this is you have this is a modulation strategies and so on and so forth. This is the positive cycle, this one, and negative cycle. This one, and you have a switched capacitor. So this is basically you can see the suppose C3 is basically the virtual capacitor, and C1 and C2 are the charging and discharging capacitor. This is known as the virtual capacitor C3. All right. So C3 will provide for the negative charge cycle. So basically, in this case, what we normally do is we need a H-bridge inverter for the negative cycle. Right. In this, you don't need an H-bridge. So without using an H-bridge, you can manage the show using a C3 capacitor here. So the output here, I'm not going to explain all these things. So you have a control strategy also. You can see the output is like this, the positive negative 3-level inverter. So 0 also will come. So basically, you can see that when it is connected to the grid current, TSD, and all these things under different conditions, as you can see the lagging, leading, and all those things are coming within the IEEE threshold limits. And also you can see that the capacitor voltages VC1, VC2, and VC3, there is a minimum point here. You can see that is known as the maybe that is the longest discharge cycle basically to design the capacitor and inductors and all these things. Anyway, so this is a Plex software result. So it depends upon we have also designed the capacitor inductors and all these things and stamper circuits also. the device losses also you can see. This is the efficiency versus output power also here. So anyway, so this is a little different topic, but I thought some value addition might be so just to show what works we are doing in the renewable energy sector also. Right, so sponsored research projects. So I wish to show some of the sponsored research projects which we are having with there are a few projects on DST and FIST and other companies also. Right, so and some of the publications which we are having in the different IEEE transactions in these things are there. So conferences also. So I think I don't want to expand it, but I thank the Bosch team for this great opportunity, and I'm always looking for motivated minds. Like my students, I have some students also PhD and Tech, etc. So I'm looking for candidates who are very keen and motivated to do PhD and Tech and all these things. And also, in our research group, we have a huge requirement also for all these things. So yeah, so this is about brief about the different type of works that we do and these publications, etc. And yes, I will be very happy to answer any queries or anything to my abilities. If I am not sure about something, I can later on also connect with you through emails or anything like that. And so this is the thing. So I think I have completed in time. So I will be happy to answer if any queries are there. And thank you so much. Yes.
Thank you so much, Dr. Jeevanand, for that wonderful talk on AML applications for fault diagnosis for electric drives. So one question would be for the students to get started with this AIML topic. So it looks like it requires a lot of training of data. So what is one platform that students can use to find this data online?
Oh, one second. Actually, am I sharing the screen now also? I don't know. I'm not comfortable with this. This platform looks a bit different to me. So
okay.
Can you unshare it? Can you unshare it?
Yes. Okay. I think we have stopped sharing. Yes.
Okay. Thank you so much. Yeah. Could you please repeat? I'm sorry, I could not.
So the question was, what platforms would students use to get this data so that they can train their models?
That's called, you need to put effort. So you need to build a laboratory. I'm sorry, I didn't show the laboratory prototypes which are developed and all these things because it takes time. So you need to put some effort in developing the laboratory prototypes for these machines, and you need to do it yourself because I train my students in the lab for doing it basically, and we do it in local workshops, and the workshop people are not trained, so we train them also. So that's how we do it. So it doesn't take much money to do it, but you need to know what to do. So you know, develop these things in the lab, and then you can build the prototypes and kind of things. So a little bit knowledge about the machines is required, like the winding configurations and three-phase winding, how it is, like the MMF waves and this three-phase winding, how it is bound basically. Otherwise, you should be able to identify the neutral point, and then only you can actually take the tappings and etc. So these things are done, but I have trained a few of my students, so they did themselves. So there's particular paper which I discussed today is also that prototype was done with that student only. So that's what we develop the prototypes, and this data is not available anywhere. I haven't seen that data available because it's very specific. Because it's not like something it's not very general data like which people use. Like I don't know, some machine learning enthusiasts, they use certain particular data to benchmark their algorithms, right? So that is not the kind of application. This is very specific. So certain community who is actually working on it only may use it. So that's why maybe these data, and I think unless you generate the data yourself, you cannot actually infer or actually conclude correctly what is coming out of it. So it's not a computational method only. So it's much more than that. So inference will not come unless you generate the data yourself, understand it, and then you predict it. So that's the point.
Okay. Thank you, Dr. Jevans, for that wonderful session. So I will now hand over it to Praveen to introduce our next speaker. Yeah.
So can I join or something? I don't know. I need to leave the session right now. I don't know
Yes,
how
you
to
can leave the session. There would be a control panel. If you click on close button, you can exit out of the meeting.
control panel. Okay. Thank you so much. It was nice interacting with all of you. Thank you so much. Yeah.
Thank you, John, sir.
So that was an interesting session. So up next we have Prashant. So we met him earlier. He was our head of COE electrification from Bosch, and we have Prashant talking on the topic of blockchain and EVs. Prashant. Hey, welcome back.
I share my screen.
Yeah, right.
Is it okay?
Is the screen visible yet?
No, we have to make the pit stop.
Okay. So I'm just finding the right screen. Can you acknowledge if you can see my screen?
Yes.
Okay. See, on a lighter side, guys, I am meeting you in the breakfast today and in the lunchtime. Yeah. So just before lunch and after lunch, it's a toughest session to take. Yeah. So I beg your pardon. Stay with me for 15 minutes. Yeah. And I will tell you about what is a blockchain. Yeah. So 15 minutes, blockchain will take some 1 year to build one. Yeah. So 15 minutes, the challenge for me is that I have to explain you why a blockchain is required. What is a blockchain? Yeah. I have to show you with some demonstration. Yeah. And I want to tell you one application, how it is implemented. Yeah. So in case you pick a project in this line, you can build it. Yeah. You can build it. You can connect the application. You can understand why you are building this application and you can apply it. Yeah. So the whole context of this thing is it's a simple technology. Yeah. But the underlying math is something which can be troubling. Yeah. So I don't want to get into mathematics. So none of the algorithms at the implementation level, the hashing, all these things are discussed here. Yeah. So I will touch upon why, what, and how through an application point of view. Yeah. So what is a blockchain? So there are a lot of hype. Yeah. Yesterday evening, I got a mail from one of the e-learning platform they were just marketing their blockchain program. Yeah. They were promising me that how much jobs are getting created. Yeah. A lot of things, the Bitcoin, there are a lot of YouTube, flags getting for Bitcoin billionaires they are telling. Yeah. So there is a lot of hype around. So what is this exact technology? Yeah. So had it been a physical session, yeah, I would have taken some answers from you. Yeah. So it's virtual, so we have to live with it. Yeah. So just let's understand what is the root. So back in 2009, I passed out from my college, yeah, bachelor's, and we were finding it very difficult to get a job that time because we were in recession. You know, a recession is like, technically speaking, in a country get into its GDP negative in two consecutive quarters. Yeah, we call it a recession. Yeah, I'm not explaining GDP what it is. Yeah, but at the nutshell, layman level, what is this exactly? So this exactly is that these people, a lot of companies are giving loans at that time for the people who cannot show anything. Yeah, who doesn't deserve. Yeah, in a blunt way. And so it reached a point where they cannot repay the mortgage whatever they bought. Yeah, so the complete system failed. Yeah, and it started a recession. It was in 2009. And the same year, one savior, or to just to make it in a bigger way or a grandiose way, something popped up, and it is called blockchain. Yeah. So, Jason, you can see my screen. It's just going into blank. Yeah. 1 second. Yeah. So it's called Bitcoin. Yeah. So what is blockchain exactly solving? It's exactly solving a problem where you have more than two parties doing a transaction, and both of them doesn't believe each other. Yeah. And it is in a way a system or a GUI, I would say, yeah, a graphical user interface which solves a problem of the trust between these two people. Yeah. And it is done using a particular methodology. Yeah. So like I pointed out, blockchain started from the recession, yeah, during economic slowdown, and then came as a savior. There is one guy who didn't yet reveal his actual identity, called Satoshi Nakamoto. He launched a Bitcoin concept. Yeah. So it was around in 2009. Yeah. And you might have heard blockchain, Bitcoin, and all. Essentially, these two are different things. Yeah, Bitcoin is just something like an app, you can say, yeah, or something like an asset, yeah, or a technology. But the underlying aspect of how it is done, it's a horizontal called blockchain. Yeah, so Bitcoin is just an realization of blockchain. Yeah. And you might have heard about cryptocurrency also. Yeah, like Bitcoin is a cryptocurrency, just like our rupees, it can be used. So these set of currencies typically called fiat currencies. Yeah. And currently this is widely used into tracking of assets, or say wherever you face a trust issue in any transaction, it is where blockchain is being used currently. Yeah. And so it is a way in which you are establishing trust through an algorithm. Yeah, you don't need to believe me. For example, myself and say Amaya is doing a transaction, and we don't believe each other. Yeah. So we need a third party or set of third party to establish a belief among ourselves. Yeah. So this is what blockchain is doing. Yeah. So literally, you are pushing the trust factor out of a person into a system. Basically, system combined of more than two people or two organizations. Yeah. I will explain a little bit detail. At the higher level, what blockchain is creating is that it is killing the monopolies. For example, like in 2009, none of the single bank could take a decision. Blockchain involves a lot of players. So whenever they are taking a decision, they need approval from democratically from most of the players. I would say in a higher level. Yeah. And it is a most secured platform, because whenever you transact something, you are putting some records. Yeah. You think it like this: you are putting some record somewhere. Yeah. And this record is being published to everyone. So when Amaya is giving me $100, yeah, or 100 rupees, and Amaya is putting a mail to everyone of you in the chat. Yeah. So that every one of you know that Amaya has given me 100 rupees. Yeah. So Amaya cannot tell that I given you 200, because it's visible to everyone. Yeah. So similar algorithm works here. I will explain a little bit more. And so complete decision is not taken by single person. It killed the monopoly. Yeah. And it is very easy to scale it to the next level with a set of algorithms which has been implemented with. Yeah. So I will explain this thing. So fundamentally, just understand this thing. So this is a technology to establish trust among people or organization or any business who doesn't believe anything mutually. Yeah. Then there is a textbook definition. So the textbook definition says blockchain is a shared, immutable, distributed ledger, yeah, that records the transaction and track the assets in an immutable, accurate, secure, and transparent manner, yeah, by using a distributed, democratized, and decentralized approach to creating trust. Yeah. So it's a textbook definition. What it means is, it doesn't hold, assuming I am an organization, I am a bank, let us assume, yeah. I have the data of all yours, yeah. I have the financial record of all yours, and how much money you deposited, I have data. And none other parties have this data with us. So the complete monopoly is with me, the data is with me, but when it comes to blockchain, it is not with one body, it is with multiple bodies. Yeah. So the data is been transparent. At the same time, it has been secured through a particular algorithm. Yeah. And it is immutable. For example, so that is the meaning of shared. Immutable means whenever I entered some transaction, it stays. Yeah, nobody is going to change it. Yeah, so nobody can correct it. For example, you can cut, paste, delete. Nothing is possible. If you did a transaction, if you did an entry into the record book, I would say it is recorded. It stays for long. Yeah. And how it is used, for example, it can be used to track anything. Yeah, I will show you one application, you will understand. Yeah, so from end to end you will get a complete list of how it is being used. Yeah, and it is distributed, so these records are not kept in one position. It is distributed among n nodes. They call it n nodes technology. Technically it can be an organization, or it can be within an organization n computers. Yeah, so that once one node is out, you have duplicates of these slides everywhere. I mean, this data everywhere. Yeah, and this is a decentralized and democratized process. In a sense, whenever you're taking a decision, yeah, for example, take a decision that Prashant should pay Amaya $100 back. Yeah, so this is something someone should approve. Yeah, exactly, it is $100 because she given me $100. I have to pay her $100. Yeah, so this transaction someone should approve. So this is approved by a consensus mechanism, what blockchain calls, because it's not by just by saying or showing some record. Some multiple bodies have to understand, yes, it is $100. Some records have to vouch it is $100, and you have to say, yeah, that is what democratized and decentralized approach means. Yeah. So what blockchain literally did is, it is a world as of now. You have a company who has the authority of complete data. Take the case of a bank, yeah, and who has the complete business logic. For example, how much interest I should pay to you. Yeah, so let us assume it's a universal decision taken by, a unanimous decision taken by one set of banks. Yeah, then I have the complete control of your asset, whatever you deposited in me. Yeah, so your complete trust with me depends on my organization's credibility. There is no technically system, some way to establish this in a paper or a record. Yeah, it's just the relationship between us. Yeah, so what blockchain created is that the one company, let us assume it has been split to multiple companies, say 3 companies. So ledger is the set of data. Here the data mean, we can just call it ledger for time being. Yeah. So the data, every company has the duplication of this data. Yeah. And they have a set of consensus algorithm, a logic which has been shared with everyone. So I cannot have my own logic and I can tweak there, because I need to share it with other companies also, so that the logic is known to everyone. That we call it a smart contract here. Yeah. Then the third part is called distributed network, because the control is unanimous here. In this particular system, none of the control is unanimous. It has been distributed across. Yeah. And the fourth one is trust is through connection. Here there is no trust required. I mean, it is a trustless system, because you don't need to believe the credibility of a bank, because everything is transparent. So the system as such will ensure the trust. Yeah. So it is a complete paradigm shift of what we believe currently as a transaction in banking firm. In other firms, we will see the application, and into a firm, into an organization which is democratized. Yeah. So let's understand how it is done through a small case study or small transaction example, because I was telling transaction, Bitcoin, all blah blah things, you may be confused. Yeah. So I will show with one example how it is done. Yeah. And this would be interesting, because you can take up any project, yeah, to track and component from end to end and build your own blockchain, because these are free. Yeah. You know, you don't have to pay a huge amount. This is a simple technology you can demonstrate with a minimum investment, and you can scale it from as just a project to a startup even. Yeah. So I will explain how it is done. Yeah. So the credit goes to this credit of the presentation, or some figures I have taken from Energy Consortium in US. Yeah. So one of my friend Tony shared the slides, so I will credit towards him. Yeah. Let me explain. So there are 2 people, Andy and Bob. Yeah. So Andy want to sell some items, let's say widgets, whatever you tell, potatoes, widgets, whatever. Yeah. And to Bob, So, and the cost of one item is $1. So Bob has to give him $3. Simple. Yeah. So, but the Bob does not believe Andy. Yeah. And he created a system or a blockchain where he need to do this transaction. Yeah. So he created a system with the three companies of company A, company B, and company C. Yeah. Whatever we explained in past slide. Then he entered this transaction after digitally signing. Yeah. So whenever you are giving have you seen our normal Indian rupees notes? It has a signature, states that I am giving you this money and this is worthy or something like that. Yeah. So similarly, you digitally sign and record in a database. Yeah. Take it as a database. Don't take it as a ledger. It's a complicated term. Yeah. So that is transaction X. So transaction X is recorded through $3 given from Bob to Andy is being recorded here. Yeah. Now this is only with one company. Yeah. Then it doesn't form a blockchain. So it has to go to complete through cycles of complete nodes, I would say, or companies. Yeah. And it has to have a copy in everywhere. So what the company A will give this transaction or translate this transaction to company B. Yeah, company B will have a consensus or a smart contract where we validate this particular transaction. Yeah, we are not checking how we are validating. It will check whether this is the transaction done or it is corrupted. Then it say yes, this is the transaction. It records the same copy in its database called ledger, and it repeats for company C. Yeah, so the transaction created by one company by but after one exchange of goods, yeah, he's been translated and copied into other two companies. So everyone has the data, no one can corrupt. Yeah. Then what happens after it reaches the company C? Then we enters into a consensus mechanism where everyone has to check that copy with everyone is same. Yeah, it's not individually they are checking. Everyone has to have a common agreement which says that the data or the copy of data whatever we got are same. Yeah, so that is done by specific consensus algorithm, what we would say. Yeah, so it doesn't do only for one transaction. There will be many transactions like X, Y, Z, and or it takes some n number of transactions. Yeah, and it will have some unique address. Yeah. So it's like if imagine if you have a multi-dimensional or multi-unit, say multi-digit number, which will be converted to a uni-digit number or a same number of 32 bytes number. Yeah. So that is hashing algorithm. So you have a unique combination of this number, and it's just a number to understand that. Yeah. And you create this block of all this transaction, telling that all are validated, and I am vouching that this is correct. Yeah. This is called a block. Yeah. So the red one, what you can see is a block created out of one of the transactions TX. It will have TY, TZ, everything. Yeah. And this is not yet blockchain. So this is just you are recording the data and you are someone is endorsing the data is correct. Yeah. Now, after you did all these things, this block will be transferred to other chain. Yeah, for example, so let us assume C is creating the block. It need not be company C. It can be any other companies, it can be B, it can be A. It depends upon a certain combination called certain different algorithm. Who decides is decided by a term called mining. Yeah, I'll explain it. But otherwise, let us assume here C created this block. It is being translated to B. Yeah, and also it has been copied to ledger A, the same way which we did the ledger transaction. So this particular red thing is called blockchain. Basically, it's not the complete the blue thing which you can blue lines which you can see here. It's the red line. Yeah. So one block is created after a set of transaction validated by multiple person through multiple algorithm and is recorded in one block and one particular node and the copied in all other nodes. Yeah. So important point to note that it is not just one transaction. It can have multiple transactions. So you are efficiently using the space of one node. Yeah. And this red particle or the red line or the sequence is what we call as blockchain. So it stays, it is immutable. Whenever Andy want to check like how much was the transaction done way back, he can come to the block and check. There is a different mechanism. Yeah. Whenever Andy is applying somewhere a loan and he is telling that I am a faithful customer to Bob, Yeah, and he needs some endorsement from someone. Blockchain can tell this. Yeah, and he did so and so transaction in the past properly, and he's a credible customer. Yeah, so this is a permanent data record which is systematically verified and stored as per a defined protocol. Yeah, so this is blockchain basically in a nutshell. Yeah, so what I explained is what is blockchain, why it is required. Yeah, and also how a simple transaction will flow through. Yeah, this has lot of depth actually. Yeah, for example, I meant hashing algorithm here. To how to create hash itself is a complex problem. Yeah, so you can have a research in one of the application and see how you are applying blockchain for one particular use case. Yeah, I will show you one use case. I will take another 5 minutes. I think I have another 5 minutes, or I will close in 2-3 minutes. Yeah, so see, I told the technology blockchain, a buzzword, Bitcoin, and lot of transaction, lot of terms I told. A simple way how you apply for an automotive industry. Yeah, this is a common application. Yeah, by the way, it's not just a Bosch topic. Yeah, so you can get it in internet. So I am making a blockchain. Wherever I told a company A, B, C. I have companies like one is a supplier. Yeah. One is a manufacturing company, the car manufacturers. One is the car distributors, basically. One is the service company or the dealers who is giving this thing. Finally, I am buying it. Yeah, I am the customer, the next person. And finally, after 15 years, I am scrapping the car. I don't want it. Yeah. So I made a block with all these people. Yeah. Then I ensured all the transaction happening between these people are recorded in a blockchain through a consensus mechanism. Yeah. So supplier give the components to the OEM to make the car, and OEM give this particular car to the distribution center as a bulk to distribute to the dealer, and the dealer hand over to the customer. Customer go through a pattern of usage. Yeah, there will be a lot of transaction happening between customer and dealer, and finally he is scrapped to the scrapyard. So complete like a transaction, you can call it anything. For example, you are recording part number. Yeah, of the subcomponents of the vehicle in a systematic way. That is one application. Maybe for electric vehicle, you can have the battery health between tracked in throughout the chain. Yeah, for example, battery is been the component. Let us assume supplier is giving battery cells to this guy, and he's making the battery, and he's integrating in the car. Yeah. And let us assume OEM is packing the battery from supplier. Yeah, and then he's continuing with the same chain, and assume a case where customer went to some other dealer, not this entire exact dealer, authorized dealer, and changed the battery, service the battery. Yeah, so let us suppose he changed something. Maybe he replaced a cell with a duplicate one or a counterfeit one, and he tried use cases and the car exploded. Yeah, let us assume the car exploded. So who is going to, when they verify where is the transaction existing? Yeah, because a car exploded, you don't know what happened. So imagine the complete track record is kept in a blockchain. Yeah, so you will understand that yes, there was a transaction which is not authorized in the blockchain, which happened with some other customers or some other players outside blockchain, and this is not authorized. Then the investigation will fall into this leg. Then they can find out the root cause. So this is a game of establishing credibility within either the supplier or OEM or the dealer, or the credibility of even the customer. One more extended use case is scrapyard. Now, when you go to a scrapyard, you will sell everything per kilo iron value. The scrapyard owner don't know the cost of magnet, lead, cobalt, anything. Yeah. So if you bring in a system in consensus algorithm, he can exactly derive the cost of this particular scrap component. So these are extended use case, So basically what I mean to say that this is a typical blockchain application you can try out. Maybe you, whenever you're doing a project, you can parallelly build a blockchain. Yeah. You buy a controller, you buy a motor, you make something, and you enter all these data in a blockchain and make a parallel stack over it. Yeah, and try to see if you can find a good application between these things. Yeah. So what this particular system in this particular application did is end-to-end tracking of any components and identifying the counterfeit. Yeah, which I explained. and implemented scrapping policy or recyclability. Yeah, for example, government insists that batteries should be scrapped in a defined way. Nobody is tracking, so but a blockchain is tracking, and you can impose penalty, you can impose the regulations, everything can be done through this blockchain. So this is a technology in evolving phase. So we don't know what all things we can do with the blockchain now. It's only known application. So why we put this topic in this particular workshop is we are at the same knowledge level. Yeah, for example, what I know about blockchain you can learn in another week or 2 weeks. Yeah, so we all are beginners. So this is a window you can explore and come up with some solution. Yeah, and thank you guys. That ends my presentation. And I understand that there is no time for question answers. You can give the questions to Jason or Ameya. We will get back to you after this particular workshop. Yeah. Thank you.
Thanks, Prashant, for that wonderful session on blockchain applications for EV. So to all the participants who are here, we have now a 1 hour lunch break for you guys. So please go ahead, have your lunch, and you guys can meet us back here by 1:40. And in the meanwhile, let me just share. Yes, we have some testimonies from our last year judges and also winners, and you can learn from their stories as well and be inspired. So we'll meet you all at 1:40.
Oh, Jason, the screen is not cropped correctly.
Oh, okay. We'll fix that. Yeah, we'll fix that. Okay.
Bye guys. See you at 1:40. My voice is so weird. Okay. നിങ്ങൾക്ക് വിശക്കുന്നുണ്ടോ?
ഇല്ല. സിനിമ ഉണ്ടല്ലോ.
കുടിക്കാൻ തോന്നുന്നു.